what it is we're doing, and get guidance from them on which parts they would like to see proved, what are the threat models they're worried about. And so these tools being a capability for us is incredibly, incredibly leveraged. Another example, so on the economy of scale, like Amazon and AWS are just big economy of scale company, right? They get big and then they find economies of scale and then they just relentlessly drive those things down so they can just offer stuff for cheaper and cheaper and cheaper and deliver it faster and faster and faster. And for the government, that's great because now they get that service for cheaper and cheaper and cheaper and faster and faster and faster. So that's the idea. Okay, so governments are catalysting ideas, and here's a slight difference. So I said before that the government causes products, but they also cause services. And what I mean by that is they cause things that are like a software as a service, if you will. Okay, another interesting ingredient. And so there's these organizations like the National Institute of Standards and Technology called NIST, and White House, for example, right? And so they are working on regulation, right? So the National what was I going to say there? All right, so the National Institute of, the NIST defines, for example, what it is to be a cryptographic module that's sufficiently strong enough to be used in software that then the government buys. So that's called FIPS 140-3, I think. And they define lots of these kinds of standards. And so then there's mechanisms by which organizations then try and meet that standard. And the NIST sets that. Another example is the White House has recently put out these pretty interesting reports where they're saying, hey, you should use formal methods. So this back to building blocks is saying that the components that we build software out of needs to be formally verified. And the White House is beginning to really understand formal verification. We've actually talked to them quite a bit. On the right, there's this thing about using, so they're quite interested in Rust, and well, what about the unsafe superset of Rust, and how do you handle that, and how do formal methods help reestablish memory safety if you're using Rust, and so on. So what I'm saying here is that they're adding rules and constraints for what the industry can vend back to them. But then we're helping them, right? So they're actually using our experience with the success of automated reasoning to define that. So this idea of, oh, hey, you should go use formal methods didn't come out of a vacuum, right? They were watching the success of formal methods in Amazon and then using that information to then define the rules that should be imposed across the industry. So basically, we're helping them build rules also. Similar with the Rust. And then again, like the NIST organization has asked us for information about how we're using automated reasoning, because what they would like to do is they would like to make that process for getting certification much less manual and use programming languages and formal methods techniques. So the point here is that we're also helping them build rules. Okay, so now we've built this insane graph that has so many details it's meaningless to you. But I wanted to, the size of it is kind of the point I wanted to make, that when you're an academic, when you're starting out in your PhD, you're like, oh, great, I write research papers, I go to conferences, I give talks, right? And then magic falls out of the sky. Who's paying for it? I don't know. But what's really happening is there's this whole machine happening that's been going on for many, hundreds of years. Way back in the day, kings had problems. Some other kingdom was like harshing their mellow. So then they asked some smart person in the kingdom, could you help us figure this out? And it's like, oh, you could only visit this many bridges in this many ways because of such and such. Thus, if the invading empire were to come try and attack us, then we could defend ourselves this way. Great, thanks very much. And then someone else in the kingdom was like, we could use that idea, like the Pythagorean theorem, to like measure tax stuff, right? So it's always been that the government, the sort of research brain in people, and then the let's make money brain in people are in partnership, and that's been mechanized in the US, but also in China and Europe and so on. Okay, so that's by country. I wanted to basically tell you the same story, but now by research topic. So here's a pretty fascinating. This is a report. It's a tech report from 1958. But it was a report to the National Security Agency in 1958, which is the basis of stat solvers, like the start of stat solving by Davis and Putnam. The original Davis and Putnam idea is started, the first place you can ever see them saying, hey, maybe we could actually solve propositional satisfiability with computers, is in a report to the National Security Agency, 1958. So why was the government worried about satisfiability solving in 1958? Well, if you remember in 1957, Sputnik happened, right? So I wasn't there, I wasn't alive. I was very far from being alive. But one could imagine that they were like, oh shit, like what if the Soviets figured out how to make P equal to NP and we don't have that capability? Think about all the horrible things that are gonna happen. And that's something similar to what's happening in quantum today. So many organizations are investing in quantum, but they don't want to be. They're just like, well, what if someone else does it? So we need to do it too, such that we're like, so they can't get ahead of us, right? And so I would imagine that was what was happening. But anyways, they funded it, and that work started off what became, for many years there was this tool called GRASP, which was sort of the most successful satisfiability solver. When I was doing my PhD, it was GRASP was the tool. Then I went to work for this company called Prover. So for then maybe 5, 6 years, the satisfiability solving was a big industry. Like I made money, and like we were making a lot of money selling satisfiability solvers to aerospace and reasoning about railway switching, and Intel bought like 10% of Prover, and all the Intel circuits. That's where I got my start in this field, was actually working at Intel. So then Prover hired me because I understood Intel circuit design and knew people there, and like great, we're going to be applying sat solvers to hardware, and all was wonderful until this paper came out. So this paper cost me my job. So it was 2 undergraduates on a summer project at Princeton figured out that if you changed the data structure that kept watched literals, you could align it with regards to cache lines, and suddenly the sat solver would, even though the sat solver in theory the algorithm didn't look like it was as good, it was a total game changer. And so this solver was much better than what we had commercially, and so the sales just began to plummet, and it was like, I need to go find a job. So then what happened then is that for 20-something years, you just got, the academic solvers got better and better and better. So this is a graph of the winner of each international SAT competition from 2001 when the SAT competition started until 2020, compared on the same benchmarks using the same hardware. So you can just see the solvers getting better and better and better over time. And that's the story, then that's what we went to Amazon. We built a lot of tools based on this. I won't belabor the point, but all customers of AWS are essentially customers of SAT. They just often don't know it. And then the deeply influential types and the security-obsessed organizations often do understand the benefits of it. And there are many stories like this. I could ask me for the Q&A for more if you want. But for example, the head of application security in Goldman TA'd Andrew Appel's course on theorem provers, right? So you very frequently are at these security-obsessed successful companies, and you realize the people you're talking to knew Zohar Mana or something like that. So they often understand what's going on. And that led to things like this, where Goldman gave a talk about their use of formal methods. Okay, so, right, I kind of made that point. So yeah, so tying the story back, and this is, I've already alluded to this, is that AWS is making much more money because we're invested in formal methods, and the Department of Defense, really deeply, influential people who make decisions in the DoD understand quite deeply formal verification. And remember, this is not just America, right? This is true in France, this is true in other places. Okay, so how am I doing for time, by the way?
No, you're doing good.
Okay, good. Yeah. Okay, you were spooking me because I was like, oh wait, I thought I was about out. I'm like, I'm nowhere near done. So, great. So then one point is that there's kind of a new shift. We'll see if this turns out to be true. But SAT solvers, I believe, are going to move back to the emotional heart is going to move back to industry because of this line here. So there's this tool called Malab. Hold up your hand if you know Malab or Malab Mono. Yeah, this tool is outrageous. This is the LLM of, this is the open GPT-4 of SAT solving, if you will. So this how you read this graph is, so this solver could solve 275 benchmarks each in 400 seconds. And that compares to the best solver, other known solver, which in 400, they could only solve 125 benchmarks each in 400 seconds. So it's just otherworldly. How is it doing that? Well, it's distributing search. It's using multiple machines. It's not just on a sequential microprocessor. It's hundreds of machines all sharing lemmas as they're doing solving at the same time. So it's just wow. But to operate this is a really different game, right? Like if you have a fast sequential stat solver, you can just write it in C, put it on GitHub, and you're done, right? But to operate these distributed solvers, you now need a team because it's a cloud-based solver. So basically, it's my belief that what we'll see is that things are moving back in the industry. Okay, so to wrap the story up, stat solvers went from government to academia to industry. Then the chaff paper came out. Everything moved back to industry or to academia, and then it moved to. I think it's going to move to industry. Similar story for the COVID vaccine, by the way. That was actually a big DARPA project. So the messenger RNA funding 2013 to Moderna, 25 million. And then like we all know that story. The same with personal computers, GUI. So many people are like, oh yeah, I know the story of like the mouse and GUIs. Steve Jobs went to Xerox PARC and saw it, right? And he built the Apple. Well, the story actually goes way back beyond that. So actually, at SRI, funded by ARPA, which became DARPA, that's where that work began. And so this is a talk from 1968 showing you the mouse and what you see is what you get, text editing and all the things you use today on your laptop. It was available in 1968. Same with the cloud. That was all fun. That was all like the military all had. It's a version of the cloud, and all that's just moved kind of into available to all of us. So, anyways, I don't want to belabor the point. Okay, so now in the time remaining, let's look. I've never given this talk, so I'm not going to make it on time. Okay, so let's just look at my career really briefly. So I did my PhD. It was funded in part by U.S. Air Force and Intel. I was at a place that was, so it's Oregon Graduate Institute, which doesn't really exist anymore. And why doesn't it really exist anymore? It's because it was on soft money. So it didn't have a big endowment, but they were getting a lot of money from DARPA, National Science Foundation, et cetera. And with the Clinton years and budget cuts and so on, that money went down, and then it struggled financially, and it moved into Oregon Health Sciences University. And so faculty at this university basically could keep their jobs so long as they brought in money. But that's actually surprisingly common, right? So that's going to be true at these organizations, that a part of your ability to hang on to your job is the ability to bring in money. And it's even true at universities. So there's a title called research professor. So if you look at people's titles, you'll sometimes see research professor. And what you'll see is they teach a lot less, but they typically don't have tenure, and the existence of their job is predicated on their ability to bring in money. So my advisor was John Launchbury, who was a big Haskell person. He went on to form Galois, and they wrote this tool called Cryptol, which was funded by the government and in use for government contractors, which then we later used in Amazon. Okay, so then what else I want to say here? So I did an internship, which I highly recommend. Basically, like if you're doing a PhD and you don't go do an internship in industry, it's a big mistake. I highly recommend it. I met these three guys when I was doing my internship in the late 90s, who I now work with today. So then I was 10 years at Microsoft, 10 years at Amazon so far. I wouldn't normally point this out, but these were promotions. Yay me, right? I got promoted. But the reason I'm mentioning it is one thing that's really interesting about the industry is that promotions represent very significant pay increases. Like at university, your pay is kind of going to look like this as you grow, right? You start here, you retire here. Whereas for me, it's like this, right? Like it's many zeros are added to the checks. And so that's something to keep in mind when you're moving to thinking about industry. And then I've built kind of a mixed industrial university career, which has its benefits and downsides, which we can talk about during the Q&A. With encouragement from Peter Ahern, because he was actually at the university I joined, and he and I decided to move to University College London, but he also visited me as a visiting researcher at Cambridge. And then I've raised, I don't know, like 10 million pounds, 15 million pounds over the past, I don't know, 15 years or something like that, to pay for postdocs and travel and these kinds of things. Okay. With the time, so when do we need to wrap up? 5 more minutes. Okay, yeah. So let me allude to some things you could ask about in the Q&A. What's that? Okay. So I have various thoughts about the upsides and downsides of academia. They have to do with about job stability for you is great. Job stability for other people when they're not very good sucks, right? Because that means you're working with a bunch of people who aren't very good. And that's kind of often what you see in the university. And so a lot of the problems you see in university are about the fact that this professor for the next 20 years is going to work with this other professor, but everyone knows that other professor isn't very good, but there's nothing you can do about it. Whereas in private industry, in industry, and that, by the way, that's true in government too. In industry, that doesn't really happen. So industry is much more dynamic, it moves really fast, but on the other hand, you get a lot less job stability. So there's pros and cons there. Yeah, so I won't belabor these points because due to time. I'd say that industry, you get less intellectual autonomy because you typically do need to work on things that are going to affect your company, right? Like I'm not going to go work on art tomorrow or biology tomorrow. I might, but I would need to, within Amazon, move to the team that's working on biology. I'm not going to be in the work in AWS and then work on biology unless there's a customer sort of worried about biology. So that's the difference. And then one thing that's kind of happening is that there was these sort of classic, basic research labs like Microsoft Research, where I worked for 10 years, which have basically gone away. They're kind of there by name, but they don't exist like they used to. And there's some reasons for that. But I think it's basically corporations don't want to pay out for far out research. I think there's probably going to be a bit of a pendulum swing. So maybe this will come back someday, but right now that's not really the reality. So what happens is Amazon and Meta and Google kind of distribute this research, right? They let every team themselves, they're like, you can hire a researcher if you want. It's your money, right? And so Amazon teams will hire what we call applied scientists, and if they bring value, then that's great, and if they don't, then game over. Okay, and so then, but I did want to say that there's been tremendous value from those basic research, and so here are the current Amazon employees, bottom, that were all interns at Microsoft Research who were in the formal method space, both at Microsoft Research and Amazon. And on the top left are the former MSR researchers who have joined Amazon. Okay, so I won't get into that. Okay, so I'll take a few more minutes, great. So I wanted to kind of close with the point that my network is my biggest asset by far, right? It's how I learn about, I tend to find combinations between things. I realize like, oh, you can take Farkas lemma and combine it with this Ramsey's theorem based thing, and then you do this other thing, and we can convert that to SLAM, and then voila, there's like 100 lines of Perl, and suddenly we have a tool called Terminator, right? That's kind of how Terminator was born, and it was because of who I knew. More impact because again, you meet people who realize how your tools can be used. Better careers prospects for obvious reasons, right? Because it's like that's how you get jobs is by. I've never gotten a job I just applied for. Every job, even when I was a dishwasher, when I was like 14 years old, was because someone said, "Hey, do you want a job?" Right? Whenever I've applied for a job, it hasn't gone very well, right? It's always like someone is like, "Oh, there's a job you should know about," and then like the application process is just kind of. Whatever. But the university professorships is a slightly different case, but everything else has been like that. And then I particularly have found that there's really great value at working kind of the liminal space between government, academia, and industry. So go build those relationships, right? Go do summer, if you're a student, go do summer schools. Go do Marktoberdorf, for example. Visit other institutions. People you meet here, set up time and go visit them. Like go travel to their institution, give a talk. It'll be a horrible talk, it's fine. Everyone will be like, hey, do you remember that horrible talk you gave? Yeah, okay. But you're meeting people and you're gonna go to lunch with people and you go to drinks with people and like that, and then those friendships you'll make, that you'll go to Marktoberdorf, then 10 years from now, they'll be the person who writes the letter of recommendation for you to get the job or the next job, right? So go build those links. Do internships, do 2 or 3, okay? Don't do like 10. and come back to your PhD, finish your PhD. Tool-specific Zulip channels, come to workshops, obviously you've done that, so give seminar talks in your university, sign up for things, give talks. Don't, screw them up, it's fine, but give the talks. That way people begin to know and they'll know who you are and you'll learn and grow. My first talk was a complete disaster. I can tell you about it in the Q&A. And then when people come and speak, go and ask questions and go to dinner if you're invited, and so on. Okay, so with that, one final point is we're hiring. So if you're looking for an internship or a full-time job, let me know. And below there is who you'd contact to set that up. So thanks very much.
So the floor is open for questions.
What was your first talk like?
Oh, okay. So I gave a talk. I was a first year PhD student. It was on System F, and I had a black marker and a whiteboard, and I was whiteboarding. But then I was like rubbing, oh no, that's not what I meant, X, I meant Y. So then I'd black over my hands, but then I was rubbing my face. And then about 10 minutes in, my professor was like, hey, I actually just need to stop you. Like, you look like a mess. And so I had to go clean up. But no, I mean, everyone was very kind about it. That's the first time I've heard that story in like 20 years, so it was fine.
So I have a question. Yeah. So your current affiliation is being both professor and industry. So do you do active research as a part of academia, or how do you even balance these two?
So I am doing biological work, and that biological work is happening at the university right now. So I've kind of, the university doesn't own my intellectual property so long as I'm not at the university full time. I have the option to go to 100% time whenever I want, but I also don't want to create a situation that's really awkward for everyone, where I kind of do work in the same area. So I've kind of carved out in my mind parts of the space that I'm working in between them. And so yeah, I have PhD students. I'm not really like seeking, I don't like, ooh, I want another PhD student, right? But sometimes PhD students will come to me and be like, I've gotten into a massive fight with my professor. I'm gonna leave, but could you be my advisor? And I was like, yeah, sure, it's fine. So that I tend to take the ones that like need somewhere to go, and so that's yeah. I mean, the thing is, like, over time, Amazon has kept me so busy, and then I do twice as many trainings, like on corruption or whatever. Right? Like you have to do training or fire. I'm always doing a fire training, right? Because I have to do it at Amazon and the university, and in 2 different countries. So it's like it's a mess. So I often wonder why I do it, but I seem to keep doing it.
And just to follow up, like, can you choose between the two in terms of satisfaction? Like, which one of these is?
So it's amazing. I reported to the Chief Information Security Officer of AWS is like the world's biggest computer, right? Like. It's insane when you realize, like, look at your phone and ask where are those apps really running. It's actually on the cloud, right? Or all your like tax stuff or your flight booking, all that's actually running in the cloud. So AWS, and the security of AWS is a really important problem. So I report to the CISO, Chief Information Security Officer. And those guys there's like tough issues happening quite often, right? Like customers having a very, very bad day. It's gonna make the news. It's gonna affect their stock, and we're trying to help them. Like I've had CEOs of Fortune 5 companies cry because we help them and we save their job, right? And the AWS security and the AWS people are just like pros. They're just like super, like they never lose their mind. They never scream at each other or so on. And then over at University College London, I've seen people just losing their minds over where the ping pong table is going to be. So the political. The university politics are very intense and competitive. But the thing is, like, the HR system at a company is pretty serious business, right? If you start going around yelling at people, you're not going to be around the company very long. But the university puts up with people. It's a different situation. Yeah. So.
Yeah. Thank you.
Yeah.
Could you talk a little bit about how government and industry sees the role of publication? Like, is it something to do if you want, but they're not going to encourage it, or is it something they encourage for PR purposes, or?
So academia, like, that's your job, is to publish, right? Like that is the product. In some sense, you're producing people. You're helping universities are a place for cultural dialogue about issues, as we're seeing right now, like on the university campuses, there's big issues being discussed, and so that's sort of part of the role of the university. And then industry is there to like make money for the shareholders. And so if publication is in line with that goal, you're good. So how is it that we publish at Amazon? When I first joined Amazon, I realized that I was being pulled into all these conversations with senior leaders of the big enterprise organizations, Goldman Sachs, Bridgewater Associates, the world's largest hedge fund, so on. And what I realized is in each case, I was meeting with someone who actually knew this. They knew automata, but they were the super technical right-hand person of the chief information officer or something like that. And I realized that they didn't really care what the answers were. They were just getting a feel for the underlying infrastructure, like what is it we were doing? Did we actually know what we were talking about? And I realized actually publication would solve that. So I was like, hey, because when I first joined Amazon, they were like, I went from Microsoft Research, which is like a publication machine, to Amazon, and I was told, yeah, you'll never publish. And I'm like, okay, that's great, right? I've published, like, look at my publication rate as you referred to it. It's just like insane, right? So at some point, it's like, how many World Pop papers can you write? Psst, boring. So I was like, I'm going to go into industry and have a lot of impact. But then after a year or so, it was like, oh, actually, publishing is super useful to help at scale customers understand what's going on, but also to help academia realize where the problems were. So what you kind of see in academia is often the academics are super sharp, but they don't know what to work on. And so we can convey problems and challenge problems. And secondly, we can communicate to the senior technical people at these large enterprise organizations what's going on inside Amazon very efficiently through publication. Oh, and by the way, then I also get to tell my friends what I'm doing. So that's so I think you asked about on the government side. Yeah, there will be similar means like governments are trying to supply economic progress for their country, right? Ultimately, that's what security is basically a form of economic security. That's kind of what they're after. Companies are out to make money, and academia is out to produce students and research to help the society stay advanced.
So I wanted to ask, how do you balance intellectual property and trade secrets and stuff like that when writing a publication? I mean, what's the process there? How do you deal with that? I assume that's an issue in industry
Extremely
sometimes.
carefully. Yeah, so so I know a lot of things I can't say. There's a funny thing I've realized, that there's an inverse relationship between what you can say and how important your work is, right? Like, so there's just a lot of stuff I can't say because I just know about security things, or I know about big business deals that are happening right now because I get looped into all these discussions about should we make this acquisition, or or there is this kind of acquisition happening. How should we respond? And then by piece, so it becomes increasingly difficult to navigate. What I've realized is I've gotten more senior too. I mean, this comment I'm making is way off for many of you, but let's say as you grow in your career, you realize that like to scale, you're kind of getting rid of all of the easy decisions, right? So what I'm really doing is I'm decisions per minute. I'm a decisions per minute machine. I'm trying to make good decisions, high quality decisions. And if a decision can be made by someone else effectively, great, let them make the decision. I don't want to know about it. I don't even want to know the details. I only want to work on the hardest things. So I tend to find in Amazon the thing that no one else can quite get and the organization can't quite wrap its head around, and we need to go that direction, and I go do the work to help us figure that out. So what I find is as I've gotten older and older, the decisions on an hour-by-hour basis get harder and harder and harder and harder. They're really, really hard. And so basically, at some point, I'll have to retire because I just can't deal with it.
Oh, you said someone over there.
Yeah, somebody.
Can you share a bit how university will program like Amazon scholars? I believe good university should support their faculty if they want to go to industries, but is that always the case?
Oh, yeah. So it really depends university to university. So I've, some universities, so I believe governments, companies, and universities sometimes get off piece, they get really confused about what they're supposed to be doing, right? So universities that are trying to make a lot of money, it's a bad situation, right? Because it's like, you're not going to do a very good job of it, and you're just going to you're going to screw up the thing that you're supposed to be really good at. So if you want to make a lot of money, just go make a lot of money, like go into banking. And so you'll see universities get really clingy about IP, and they get really clingy about like, oh, you can't do a startup unless you go through our startup program, and then there's a bunch of people kind of get in the way, and like it's like if you just talked to the right venture capitalists, you would have just like really quickly gotten the funding, but oh no, now they need a piece, and now when you can make your company try and sell it, suddenly the university has to sign off, and they have tag along, drag along rights, and it's just a mess. So the other universities are super hip to this idea. They're just like, great, like intellectual property, what's that? Go for it, I don't care, right? And so Cambridge University is really good. I believe Stanford's really good, you know, and then there's other universities that I don't want to name that aren't so great with regards to that. So you really have to sort of pick. It's actually one thing when you're looking at faculty positions, it would be one thing to consider. Sometimes the state universities are a little worse with regards to this because they have to think about the perception in the public about how they're spending their money.
Can you tell us about, so you showed us that graph, and I think most of that graph mostly said that all these three components within one country, how they work together.
Yeah.
Can you tell us about like how different countries work together in that sense?
Yeah, okay, so yeah, there's another weird interconnect going on. So for example, there's this thing called the Five Eyes. If you Google like Five Eyes, you'll see it's Australia, New Zealand, Canada, US, and Britain all share intelligence, right? And there's actually like people from GCHQ, which is sort of the British equivalent of National Security Agency, can like go into the National Security Agency. They can get on their network and so on. So they share, but then there will be secrets that they keep from each other, obviously. And that happens on the university sense too. So the government agencies will often have, for purposes of creating partnerships with the other countries, pools of money. So I've actually been the recipient. One of the grants I got in the UK actually came from Brad at the National Security Agency because he's like, oh, we have this money that's earmarked for international collaboration. So like no one else in the US you can't get it, but I can give it to you. Great. So he sent the money, I think, via GCHQ. So that's common. And then you'll see that around, certain countries will decide that they're trying to build a partnership, and maybe they weren't super close, but they want to be close. And so they'll sort of or maybe something horrible's happened in the country long ago, and they're trying to like make amends, and so they'll fund like collaborative research between them. So you can then be the recipient of these things. So then in the European Union, then things get really interesting, and then Brexit and Britain, and can British universities participate in the EU thing? It's messy. So, but that happens, and it happens a lot. Sorry, I feel like I didn't really answer your question, but I'm sort of like a qualified yes.
Thank you.
Hello, I wanted to know sort of how hobbled will your prospects be if you're picky about working with defense? Like how picky can you be about working on defense with military and so on?
Yeah, so I'm reading the same newspapers you are. So just from the newspaper, I don't know anything. I'm not revealing anything, but I can see from the newspapers that Google has really tried not to go into defense. And so they actually had some contracts, and I think there was like the employees, took various actions to cause the organization to walk back some of those decisions. Amazon has not gone that direction. So here's how I think about it. I've always tried to work on tools that anyone could use, right? So I wanted to make sure that the tools were open source or had non-military applications, and so activists could use them, governments could use them, companies could use them. Great. So I'm cognizant of the fact that There's actually a slide I deleted, but there's this really great quote from the National Security Agency where it's like, why are you investing in quantum? And they're like, we're investing in quantum because everyone else is investing in quantum, right? So in some sense, that competition amongst countries creates our jobs. So I'm kind of like that. That I like the fear in the government because then now that pays my bills, and it lets me do research. So I'm kind of into that, but I don't like shooting people. So I'm not for that. So I've tried to do work that wasn't that the only application was something military. That's how I thought about it.
Yeah, I have a question. So in your talk, you sort of painted a nice picture on how industry and government together, in some sense, orchestrate the research that must be taken forward. Since you've also been an academic, and for our students to, it'd be good to understand what is the contribution of academics as independent contributors. This is unlike, a person working in a company where, the decisions are centralized. Same for the government.
Yep.
But as a professor, as an academic, it's slightly different. So what is the kind of impact an academic can make as an independent contributor?
It's wide and wild. So my advisor John Launchbury went on to build much of the early crypto Galois work was actually done at the university, and then he realized, wait a minute, I can actually just get a lot more money if I form this company, and then, right? So that's one extreme. The other is like Marijn Hule, who, for example, is just interested in propositional satisfiability, but then the government wants access to those tools. So he's not really done any work specifically for them, but they're quite interested in this work. Another example would be like Greg Morissette. So Greg Morissette sits on all kinds of boards and panels, right? So there's some, I forget the name of it, but there's some panel of super geniuses that get together to advise the federal government on what are the risks. And I'm always being interviewed for these kinds of things, right? And it's often from Greg Morissette. So you can advise the government, you can go visit the government, you can just build tools that they happen to use. You could avoid the government. So from an academic view, it's like there's nothing you can't do. I like your portrayal of my talk because it was the point I was trying to make, is that it's decentralized research. Like the world is your research lab, basically. And so there's many organizations, and if one person over here hates you, well, there's 15 other organizations, and then maybe they like you. And so you just need success in the aggregate. And so it's quite a nice space to work in for that reason, yeah.
Hi, thanks for the talk. Could you actually tell us more about the internship experience you mentioned during your talk, or as a PhD student, you going into it, and what were your thought process going into it, and then having done it, coming out of it, and how that impacted your PhD and onwards?
Yeah, so I remember when my first conference was CAV. I started my PhD in 96, 7, and I went to CAV 98, and I was just so impressed that Intel funded the proceedings at CAV. It's really funny, when advertisers go for the youth because it's very sticky. If you like that kind of drink, you're going to drink that kind of drink for many years, right? And so that was really Apple. I think someone from Apple's here. They invested in this thing, smart move, right? Because for many, many years, people will be like, "Oh, Apple's so cool because they funded that thing." Well, it's it didn't cost them that much money ultimately, and they got a tax write-off anyway. So it's actually not that big a deal. I mean, we're in the same in AWS. I'm just saying, it's a really smart investment, small amount of money, very impactful for people, because you click and you're like, oh, great, that's my brand now. And so I was very impressed with Intel, and my advisor got $40,000 from Intel. If you think about it, that's really not very much money. But for me, a PhD student, I'm like, wow, this is so, we're going to change the world. And so then it was well, as a part of that, so I'm gonna tell a slightly long story, but you can pull me off the stage if you want. So I was gonna do an internship, and all was great. And then there was this, there was a budget cut, and they were like, hey, bad news. because you hadn't actually signed your contract and sent it in yet, we actually have to kill your internship. And I was like crestfallen. But then they're like, oh, but we have this trick. Maybe we're going to try it. We're going to bring you in as a contractor, not an intern. But we'll just treat you like an intern. And so then I got this contract then, and it didn't actually have an ending date. It just said, you're a contractor at Intel. Okay. And so what was amazing is we were able to buy a house with that, because now it looked like I had a real job. So I was able to get a mortgage. I mean, the moment I got the mortgage, then the job was over. And so I then paid the mortgage on my PhD stipend, but that was pretty cool. So anyways, so I went in and I didn't know anything, and I was a PL person, and I thought monads were going to change the world, and Haskell is the best language ever. And if you're not using Haskell, you must not care about computing. And I spent my entire time trying to convince everyone they should use monads. What was really cool there at the time is they used this language called FL, which actually is a lazy functional language. And they had this whole all the design, circuit verification tools were all sort of in FL, and they built a theorem prover in FL and so on. So I thought that was really cool. And then I got really into formal. I didn't really know anything about it, but I was commuting with a guy named Don Syme, who went on to write F#, the programming language. He was actually Mike Gordon's PhD student in theorem proving. I was a programming languages person, and we were stuck in traffic all the time going home together. And so he told me all about formal stuff. So then I went back to my advisor when I returned, and I'm like, this is going to change the world, so I'm going to do this. And he, to his credit, was like, I don't know anything about that, nor does anyone here at this university, but okay. And so actually my PhD was not very successful, to be honest, because I wasn't connected. My papers all got shot down in the formal methods world. Well, not all of them, but I didn't have a great publication record. No one's heard of my PhD. In part because I wasn't in the flow. I wasn't amongst, my advisor wasn't super connected, and the other PhD students didn't know what I was talking about. But that's how it went. So I'm happy to answer more questions, but I'll stop there.
Hi, so it seemed like you alluded to this problem a little bit during the talk, but you mentioned decreasing intellectual freedom due to the disappearance of things like Bell Labs. I also work for a national lab, and I know that no matter what country you're in, your research has to be constrained to the national interests. And so I'm wondering, where do you see the most intellectual freedom in research? Is that only constrained to academia, or do you have to be in that liminal space where you're collaborating with lots of different people?
Great question. By the way, now you know someone in the national lab, so you should, if you want to get your bingo card, met someone from a national lab, go talk to her. There's this quote from Strachey. Strachey was started the Oxford Computer Science Department as a contemporary of Turing's. That says the division between theory and practice in computing is injurious, that theoreticians don't know what to work on and practitioners don't know what they're doing, basically. I mean, that's not a direct quote, but then there's the other quote is the true test of intelligence is to keep two opposing views in your mind and make progress. So I'll get to why I just made those two quotes. So I spent years seeking out intellectual freedom. I was actually a developer in the Windows kernel when I did the original Zapato, which then led to Zap, which then led to Z3. So I wrote the first SMT solver in Microsoft, but I was actually a developer in the Windows kernel team. And I was like, I've got to get research freedom. And I moved my whole family from Seattle to Cambridge, England, seeking out a job in a research lab for intellectual freedom, and I got it. And if you look at my publication record and stuff, I think it went very well. It was very fun. But then what I realized is that being kept in bubble wrap away from the real problems is not the way to go. That anyone who's successful, look at Ken McMillan, look at in my space, anyone who's doing a good job, who seems very disconnected from industry, it's kind of lying to you. What they're really doing is that they're figuring out the problems and they're abstracting them away and sort of getting rid of all the industrial smell from it, then solving it, and then publishing papers as if they were thinking deep thoughts in there. But it's not true, right? They were actually talking to people in the university or visitors or whatever. They're learning about industrial problems. So actually, I've realized sort of counterintuitively that, and like look at Turing's best work. It was like during wartime, right? So like I've kind of realized that getting out of your comfort zone, so maintaining this view that you are doing research and you are thinking about 100, 200 years out from now, but you're using the gravitational pull of the big problem of the day, the war, the security issues, whatever are the big issues of the day, to sort of drive, and you just have to find partial alignment between the bigger picture and the smaller picture, and drive on that. If you go back in history, like look at like logicians and so on, they were they were teaching high school also, right? So they were all the people were doing that also. So it's a challenge. So I don't know if I answered your question, but like yeah, that pure dream. Like, I just get to sit on my beanbag chair, and people send lots of money, and no one ever bugs me, and I'm just going to do amazing work, will just turn into nothing, because you won't know what to work on. And even, like, at Microsoft Research, what I saw was, I wasn't allowed, when I moved over to the research lab, we were not allowed, I'm sure it's not true today, so this is not representing Microsoft today, because I know there's been a lot of changes. But at that time, I was not allowed to talk to anyone in the Windows team. Why? Because the view was Microsoft Research was a massive distraction. And so I had, like, my Terminator work, like working on termination improvement, which was really aimed at device drivers, and the Slayer work, which was aimed at reasoning about memory safety of device drivers, really had very limited impact, did not become a part of the product. Why? Because they weren't allowed to talk to me. So I didn't like that. So I come to Amazon, and I have created a research life at scale. Like the things that you do at scale, if the things are moving fast enough and they're interesting enough, then you scale. And what do you scale? Well, you do the things you're really good at and are leveraged for you. And for me, those are the things that are basically I would do as a researcher, basic researcher anyways. But you know, like I know all the decision makers in Amazon, and they know me really well, and I can just send a text message and be like, we should do X, and it's like done, right? And I know about a lot of stuff way ahead of other people because of the connections I have now, and that helps me like think through things and like frame my research in a way that, like, yeah, that's, anyways.
So we are out of time, but I can't help ask this one last question.
Okay.
Selfishly.
Okay.
Were you hesitant or skeptical when you are applying formal techniques at the scale of Amazon? Because as a researcher, I build a prototype, and I'm happy if like at least 2 more others are using it, but like at the scale of AWS, yeah. I always wonder.
No, I always believed, because when I worked at, I mean, our tools they're solving the undecidable. So the only way, I didn't think of it that way. I thought of it this way. The only way to actually make progress when you're solving intractable or undecidable problems is to get even closer than you would normally need to get to the people who have the problem, and then frame it and tune it such that it works for their problems. And I learned that as I was actually at Prover, I was a pre-sales engineer. So what that mean? I went on site to companies like Cadence, Synopsys, Intel, and made the stat solver work for their use cases. And then when I worked on Terminator, it was just the observation like, yeah, I get it, it's undecidable, but it's going to work for device drivers just fine, right? And so like, so basically we made a tool that worked, and then if you look at the work, it's like 5 or 6 years of publications at Popl and Cav and PLDI, sort of like talking about like interesting formal methods-y, structural, theoretical things that come out of it. But it was driven by the idea that, like, you know what, device drivers are just like pretty simple. They have cyclic doubly linked lists. They all need to terminate. Like, I bet we could do something lighter weight. And so yeah, I thought at Amazon, I didn't realize it would grow to the size. Like, we're getting billions of requests per day to the solvers. We've got, I don't know, there's like 1,000 people in the Slack channel. There's like 20-something teams. Like, it's huge. And big zeros being added to checks these days by customers because of the work. So it's much bigger than I ever thought it would grow. But I definitely thought that like me and like 5 or 6 people would make a lot of progress. Yeah.
Thank you so much for the insightful talk, and especially the Q&A.
Yeah.
Thank you so much.
Great, thanks.
So we'll head out for a break, and we'll reconvene back at 10:40.
PLMW. In this session, we have... What? Yeah. Sorry about that. As I said, we have 3 talks lined up in this session. The first session here is from Hila Peleg. She's an assistant professor at Techion, and she's works on human-computer interaction and program synthesis, and she's gonna tell us how we can let users do the undecidable. The stage is yours. Not the end, but the clip. Clip 2. Try now?
Now, is it okay?
No, it's just making a weird noise.
Can you try this? I won't.
No, this one is... Are you okay with this?
Yeah. I only have one thing in my hands at a time, but
I'm sorry.
it's okay. Okay, yeah, so in other words, how we can take the 2 fields of programming languages and human-computer interaction and make them be friends. So as an example, let's look at program synthesis. Because we are in Europe, I am obligated to mention that program synthesis is not to be confused with reactive synthesis, which is a similar but also wholly different problem. Because we are in the year 2024, I'm also obliged to mention that it's also very different from code completions with large language models. Those of you who have done some verification may recognize this formula, which is except it hasn't exists now, but for those of you who haven't, program synthesis is the task where we have a magic box that takes some way to express what it is that you want a program to do, and gives you back a program that does that, or at least hopefully, sometimes it fails. So if we go back to the formula, what we're trying to do is we're trying to find a program from some language, and this language can be, I don't know, Python or whatnot, that upholds a correctness criterion for every input that you will give it. And so in order to solve the synthesis problem, we need to do 2 things. We need to figure out how you find a program, and you need to figure out how to express correctness. And once you've done those 2 things, you're done, right? Because that's literally all there is here. And we're going to start with the second one, because it's kind of important to know what you're looking for in order to search for it. So how do you express correctness to program synthesis? You can do it in a lot of ways. You can do a thing called sketching, which is to talk about the structure of the program. You can talk about types, which are getting really, really popular nowadays, which is to say, given inputs that are of this type, I would like an expression that gives me this type back, and this can be, simple types or fancy types, whatever strikes your fancy. We can work in logical specifications that are either full, so someone's written, a large logical explanation, or they can be partial, so like assertions in the code. And you can talk about examples, which I'm going to talk about a bunch more today. And once you've decided on that, you look at your space of programs, so let's say every possible program in Python, and you search through it for a program that meets your specification. And then we're done. We did synthesis. Yay. Thing is, this is very, very hard. Actually, if we look at the task, generate any program that exhibits whatever behavior, some of you may recognize this to be undecidable. And the more general that we are, the harder the problems become. Those of you who are already at some point into your research in programming languages probably recognize this axiom to some extent. But it's okay, because this also gives us the solution. The thing that we do is we try to scope out an easier problem. So here's an easier problem. Generate a program with such and such behavior from a subset of the language that has a program tree no larger than, let's say, 10 nodes. What did I gain by this? Well, my space is finite now. I mean, it's still huge, but it's finite. So all I have to do is look through it, and I'm good. Which still leaves the question of how do I do that? So I'm going to give you now what is essentially the recipe for practically every single program synthesis paper ever, and probably in the future, except for the ones that do large language models, which is you generate a candidate program, and then you test it against the specification and see if it fits. And if it does, you're done. And if it doesn't, you go back and you get another program. We call this generate and test. And in this abstract form, it is kind of upsetting that this is the best that we can do, but this is kind of the best that we can do. But I kind of haven't told you how I do any of this, right? So to generate a program, we can do a bunch of things. We can fully enumerate the space of programs by looking at trees, and we can do this from the leaves up or from the roots down, because every single field in computer science needs its own endianness debate. We can encode the space of programs into graphs and then do reachability problems on them. We can use deduction rules to do a proof search with backtracking. And then whenever we get a candidate out of one of these options, we can take the program and run some tests on it and see if it passes all of the tests. We can encode it for an SMT solver and see whether or not it says SAT. And we can apply typing rules and see if the program types correctly. And if we just iterate through this forever and ever, at some point, maybe, hopefully before the sun runs out, we will get to the program that we're looking for. Let's take example specifications as our example. We call that programming by example, and I will demonstrate it to you by example. So let's say I would like to find a program, and I tell you all, my synthesizer, that the program I would like, if my input has X with a value of 6 and L a list 1, 2, 3, I would like to get back 18. And if X has the value of 2 and L is 1, 2, I would like to get back a 4. Have some of you already figured out what program I'm after?
Well, one possible program is you multiply X by the biggest value in L.
Okay, that could work. What could also work?
You could also multiply X by the last element of the list.
Okay, what else? Right, okay. Well, what we notice here is that I've only given you a very partial specification, and there's a bunch of programs that could fit here. I actually meant the length of the list, but that's not what I specified. I gave you a really partial specification. We're going to keep that in mind for a little bit later. So in general, I'm going to say that my set of examples is some input going to some output, many, many pairs like that, or as many pairs as the user wants to specify, where inputs can be values of variables, state of the environment, whatever comes in, and outputs can be the state of the environment, can be an effect, can be exceptions, can be just a value. And in general, this is going to mean something to the tune of, if my input is the first example, the input of the first example, then running the program will give me the output of the first example. And if the input is the input of a second example, and so on and so on. And again, you'll notice that a huge portion of the input space remains unspecified here. Now I'm going to start looking for a program. And I'm going to do this search actually top-down rather than bottom-up. I'm actually a bottom-up kind of person, but I decided for goodwill and whatnot, fairness, and it's actually a little bit easier to show. So I'm going to look at the thing that describes my space of programs, which is all of these grammar productions, and I'm going to start crunching out all of the programs I can get. So the first thing I'm going to do is produce something from my start variable. I have one option, so I have done that. And now I'm going to try to produce something out of E. And I'm going to go for like my first option for the smallest program possible. So E produces ID. And now what I have is a complete program, right? I have no non-terminals left, no holes left in my tree. Except it's not really a complete program. ID can be any variable in my inputs. So I could actually treat every single variable separately in my grammar. I could have done that, but I didn't. What I'm going to do instead is I'm going to ask the question, is there a variable that I can substitute in for ID that in the program ID gives me all of the outputs I want? So I'm going to take that question and my examples from before, and I'm going to feed it into an SMT solver. And it's going to think about it for a very short amount of time, and it's going to say no. So I'm going to backtrack. And I'm going to try the next production that works for me, which is E produces num. So again, I'm going to ask, is there a constant value that I can substitute for num so that the program num, or so the program, whatever that constant value, gives me all of my outputs, which again is no. So I'm going to backtrack, and I'm done with trees that are this small, and I have to go bigger. So I'm going to, for instance, produce E produces E plus E, and now I have more non-terminals to complete, and I'm going to keep developing those productions until the next time I hit a concrete program, and then some backtrackings later, I'm going to get to this point more or less. And I have just like that last E at the bottom there left to develop, and I'm going to look at E produces ID. And now when I go to my solver and I ask it, given these examples, can I put something in that ID and something in that ID that is going to give me what I'm after? Then the solver will tell me, yes, if you put X there and L there, then you're good. And maybe actually it found all of your other ideas before that. And then it would have stopped then rather than now. You may notice by the fact that this was an excruciating example to go through for such a simple program that this is hard work. And actually all of these things are really hard work. All of these things are not just exponential, they're exponential over like a huge space that has a lot of redundancies. And what we do, as we often do in programming languages, is that we cheat. And specifically here, the thing that we do to cheat is we take things from our second column, from testing the specification, and we fold them into the way that we do the search. And in general, the algorithmic side of synthesis research is very much focused on how to fold the specification into the search and domain knowledge into the search so that, well, it's probably never going to be any better than exponential, but at least it's going to be like slightly smaller exponent. And then maybe we might finish in like a reasonable amount of time. And you can come to the synthesis session on Friday and see how some of this is done. So, okay, we did all of this work. We selected one from column A and one from column B, and we have ourselves a search algorithm. We can do synthesis. How are people going to use this? Like, We want to give people the ability to like generate code with this. So the sad fact of the matter is that most synthesizers look like this. And the reason is that algorithms development is done, as its own field of research in PL research. And so you wind up with a thing that works and like beats a bunch of benchmarks and has really pretty graphs in the paper. But if you want to use it, you need to like open a configuration file, probably a JSON file, and you need to edit it and save it and then run an executable with it as input. And then you're either going to get like a standard output snippet of code or like in a file, which you need to open and then look at it and decide whether you like it. And if you like it, copy it and paste it into your code. Does this sound like something that you're going to do on a regular basis? Whereas we kind of know that there's a bunch of code, stuff that we use on a regular basis that looks a little bit more like this, right? And all of these suggestions and tweaks and refactorings that work here, like that feels better, right? That feels like something I'd use. Why does this feel like something I'd use? It's within your workflow. Exactly. It's part of the workflow. Thank you for that. Not a plant. The fact that I don't have to leave everything that I'm doing and go ask for a refactoring or go ask for a code completion really, really matters. So how can we do this for synthesis? And the thing is the linear, workflow that I showed you, where specification comes in and then the synthesizer thinks about it and then code comes out, that's kind of a lie. Because when a human uses these things, even if, with a JSON file and running a command line application, you have a person who thinks they know what they want, and then they communicate it to like some interface, which again can be anything from a JSON file, but it can also be like the Minority Report glove screens thing that most of you are too young to remember. And then that thing turns it into a specification that can go to the synthesizer, and then the synthesizer outputs a program that doesn't immediately go back to the person. It gets filtered in some way through the thing. And the thing is going to help the person understand and validate and think about whatever came back and see if they're happy with it. And this is not a one-off thing either, right? Because the person might be unhappy with the program because I might have gotten X times the last element of the list instead of X times the length of the list, which means that I need to give it more examples or refine my specification and go back through this iterative loop, which means I'm going to need help doing that. And this thing in the middle of all of this is called an interaction model. And an interaction model essentially is what the user sees when they see the system. It's the way we consider the system, us as developers, from the user's perspective. And so when a user is faced with a synthesizer, what is that like for them? So for a synthesizer, they need to think about how do they express what they want, and can we make that any easier for them? And they need to look at what comes back and see, is this what I wanted? And they need to think about, if it's not what they wanted, how do I recover from that and get what I wanted in the next iteration? And even what it is that I'm looking at when I'm looking at the output is something that gets filtered through the interaction. So, and all of these things, as far as the user is concerned, are interacting with the system. And we need to think about how we do them in order to design them. Because let me let you in on a secret. All artificial things are designed. So even I'm going to feed a JSON file into a command line application is a design decision. Is it a good one? Sometimes, but not necessarily. But let me give you, a suggestion of an interaction model for programming by example. So let's say I have an environment where I can look at my code. This is called live programming, where as I'm writing my code, I can see, can you see on line 6, there's an execution of the function on the top, and I get to see the values of every line of code as I'm writing it, and it's constantly updating. This is called projection boxes. And actually, as a synthesis person, I look at this and I go, oh, inputs. So I can actually let the user say, okay, well, for this assignment on line 3, I don't know what the code should be, but I would like this to be the output. And if this is the output, I send this to the synthesizer, and the synthesizer thinks about this for about 2 to 3 seconds tops, and comes back with, this is the code you want, which for me is great, because I keep forgetting in Python whether it's separator, join, list, or a list, join, separator. So hey, I didn't even have to think about that. So this is, nice and in the workflow and great, but kind of simple. And the thing that isn't simple, the thing that is nice, is that interactions can help in cases where the specifications aren't maybe as obvious to provide. And for that, I'm going to really, really speed through why loops are hard. We're going to do this as a very, very quick pop quiz to see if you're still awake. We're going to do one out of the 2 things I planned. What program am I trying to specify here? Yes, the face you're making is absolutely right, because obviously I was going for this program here, right? It's not that if you find it hard, it stands to reason that a computer will find it hard, but hey, a computer doesn't find it that easy either. We're not going to do the second example for lack of time. The thing is like this. If my loops are independent iterations, so let's say someone already told me, I would like you to do this for comprehension for me. The only thing I don't know is what the lambda actually is. And I want to go from this list to this list. I actually get to do something really, really nice and easy. I get to say, well, a for comprehension matches every element from the input to every element in the output. So I just need to synthesize this specification. I can completely ignore the fact that I'm inside of a loop. I'll take the result, I'll plug it in, and I am done, I'll be fine. Where it gets really, really hard is when I start having data dependencies. So, I want to go from 1 to 3 to 6. What am I trying to do? Sum. Okay, well, in order to do sum, I'm going to need to do s equals s plus something, right? So if I try to do this, well, the thing, if I try to do the same reduction that I did before, I know that in the first iteration, I'm going to get some value. And that value is going to get assigned into s, because that's what my sketch says. And then for that, I'm going to get some second value, which is going to get assigned into s. And then from that, I'm going to get a 6. So now I need to solve 2 unknowns before I can even approach my synthesis problem at all. This got really, really hard. So how do we solve this? Well, we solve this by putting a constraint on specifications. And this is like a really, really old solution for this. We say, I'm going to force you to give me specifications like this. For the empty list, the result is a 0. For 1, the result is a 1. For 1, 2, the result is a 3. And then for 1, 2, 3, the result is a 6. What did I do by forcing specifications that look like this? I made the user give me question mark 1 and question mark 2, and actually question mark 0, which isn't really a problem in this specific example. Thing is, if I now tell you that every time you do a specification, you're going to have to do something that looks like this, or synthesis fails, are you going to always remember to do that in your JSON file that you run through a command line application? Probably not. But let's make the interaction model, let's make it the interaction model's problem. So if we look at the projection box for this exact thing, slightly longer list. S is currently 0 for everything because we don't have an expression that assigns to S yet. And we're going to start filling it out. So, we put a value in S out. So for the first iteration, it's going to be 1. And you'll see that it immediately fills in S in the remaining rows. But now something interesting is going to happen. The user tried to tab past the 3rd line to the 4th line, and it's not letting it do that. So without the user even really noticing, it's not something that you have to really, really be conscious of, you can't give a specification that is not a trace complete specification. And it probably didn't even annoy you that much because it was just a thing that the UI didn't let you do. The thing about that is that most loops don't comprise just one assignment. Usually we have multiple statements in the same loop. So the thing that we kind of had to do once we did that is say, well, at least we're going to make it easier for you. If you need to give us the values for every single variable in the loop at once, because this whole thing of taking things from the iteration and moving it to the next iteration needs all of the values of all of the variables in the loop, at least we're going to make you not have to specify the order. Which was a really nice thought on our part, but it means that if we started out with a synthesizer that knows how to solve the problem, one assignment gets this value, we now want to solve the problem. This many variables in arbitrary order get these values. And what we had to go back and do is generalize the synthesizer by actually checking all of the possible orders. So it's, bad, but not as bad as it actually seems. And maybe the takeaway from that is that in order to have a usable interaction, you're going to have to go back and change the synthesizer too. And so now that I've shown you all of these things about synthesis, I have to ask, can we generalize this to other PL research? Because I'm realistic that the number of you in this room interested in synthesis research is probably kind of small. And I think it can. I mean, in general, our PL algorithms are hard. In general, they can handle programs of a fairly limited scope. And in general, they come with really weird input constraints. And when we do interfaces for user-computer interaction, we want them to be fast. We want them to appear general and as though they can support all of the programs. And we want them to hide and slide away all of the constraints. And by doing this mutual effect thing, where we look at both of them at the same time, we can kind of try to make sure that we do things that work together well. And this is what I do for program synthesis, and I hope to see people do this for all of the other things. It's done for some of the other things, but we should do more. Thank you.
Okay, we have time for a couple of questions. Yeah, one on the right there.
Hello. So the synthesis, if you have used CodePilot, can something like a ChatGPT be coupled with such sort of programs to give better results? Because if you ask something to ChatGPT, it would give you most of the cases it would give you wrong information. But can that be coupled with program synthesis to give out better results, or vice versa?
Okay, so the reason I said at the beginning that I'm specifically excluding large language models is that this is a 40-minute talk, more or less. The short answer is that even the easy thing I can do, which is to say I'm going to loop around until it actually satisfies the examples, kind of maybe works. Because it sometimes will give me immediately the thing that I want, and sometimes it will just be nothing even remotely related, and it doesn't check, it doesn't know. The nice thing about symbolic synthesis is that at least it knows what you asked for, and if you get something back, it's correct by construction. How you can fit that into interaction models, is, again, 40-minute talk.
I was curious about sort of the user experience when you have something that is undecidable, because like if it doesn't terminate, the user experience I feel would be just it hangs or it times out after 10 seconds. So how do you like handle those user experience quirks, sort of?
I mean, the short answer is 7-second timeout. The slightly longer answer is that in terms of the interaction being the thing that drives what the user sees of the system, if you have an interaction that encourages the user to break up the problem into smaller problems, then you've actually literally delegated to the user part of the work that you're trying to do. And it's easier for the user to think this way, it just so happens, and you're encouraging them to think this way, and then they're giving you smaller tasks to do, and then you're happier, you know, as the synthesizer. So there's a lot of back and forth in terms of the design. And yes, every so often you time out and fail, and the user is sad.
Thank you.
Yeah, unfortunately we're out of time, but I'm sure Eli is going to be around. You can also join as a mentor and for the lunch, and then we can ask more questions there. Now we have to move on to the next talk by Shyam Chakraborty. He is an assistant professor at TU Delft. He is going to talk about shared memory concurrency models. Go for it.
Thank you, Marco. Do you hear me clearly? Should I?
Speak up, maybe.
Okay. Now is it clear?
Yeah, it is.
Okay.
Oh, yeah. Now better.
Now it is good. Okay. Hi, everyone. My name is Soham Chakraborty from TU Delft, and I will talk about the evolution of shared memory concurrency in the programming languages. No? Doesn't work. Oh. Am I in the right position? Okay. Enter full screen. Okay. Thanks. Okay. So, in today's computing, as you know that concurrency is everywhere, from applications, programming languages, to architectures. And particularly with the emergence of the modern multi-core hardware, shared memory concurrency has been a dominant programming paradigm. Now, what is shared memory concurrency? So, in this case, there are different processing units are connected via a shared memory, and the data resides in the shared memory locations where the multiple threads can read and write to exchange information among them and to communicate. Now, given this system, a fundamental question has been that what is the possible executions of a concurrent program? Now, this question has been explored in several contexts, beginning with Lamport in 1979, where he answered this question with sequential consistency. So, in sequential consistency, multiple threads executes the shared memory accesses in the order of the way they are specified in the program, and the threads interleave in arbitrary manner. So overall, whatever the outcome of the program we get here defines the program behavior. Now, in reality, the systems are not that simple. There are intermediate buffers, caches, and complex memory hierarchy between the processing units and the main memory, which actually affect the behavior of concurrent programs. Now, if we consider the overall space in this area, there are some additional behaviors compared to sequential consistency. So how do we understand that? Suppose we take a program and try to understand that what are the set of possible behaviors. Let's say this is the set of behavior you can get from thread interleaving. However, there are additional program behaviors which are known as relaxed memory behaviors, and these models are overall known as relaxed memory concurrency. So to understand this, let's look at an example program, and we will use this example throughout the talk. So let's understand this. In this program, x and y are shared variables initialized to 0, and the program has two concurrently running threads. Okay? In the first thread, variable x is read in a thread local variable a, and then y is written value 1. On the other thread, y is read in b, and if b is non-zero, we write x equal to 1. And for this program, we ask that if at the end of the execution of this program, both a and b equal to 1 can be possible. Now, if we look at the interleaving executions of the program, then we can see these are the possible behaviors. So let's say we take the first behavior, a equal to b equal to 0. Now, it is possible that the read operations in both the threads are executed first, right? So in that case, x reads from the initial value 0, y reads the value 0 also from the initial locations, and then the write operations takes place. Now, if we go to the second outcome, a equal to 0 and b equal to 1, we can see that if the first thread executes this program, so in this case, x reads the value 0, y sets the value 1, and then the second thread runs, then y reads the value 1, and at the end, b is non-zero, so x equal to 1 can be written, right? But if we look at this program, in no interleaving, we can get both a equal to 1 and b equal to 1 as an outcome of this program. Because when a equal to 1 means x equal to 1 has to be executed, which is not possible unless we get here y equal to 1 to be executed. Okay? However, if we take this program and say we run on different multi-core hardware, this outcome is not allowed on x86 machines like Intel processors and so on. However, in PowerPC or ARM processor, this outcome is allowed. So the devices, for example, our smartphones and so on, which uses these processors, there this kind of weak memory behavior is possible. Okay? Now the question is that here we have seen that this is not possible in x86. So we may think that then if we are using the x86 processors, then we will not have such kind of effects for this program. Now, in addition to these processors, compilers also perform some transformations which affect the outcome of the concurrent programs. If we take the earlier program and consider it as compiled by a mainstream compiler, a compiler may look at the access pairs in the first thread, and it finds that they are independent. There is no dependency between them. They are accessing different memory locations. So for some optimization step, what it can do, it can reorder these two accesses, right? And after reordering, it is possible to have an interleaving execution when we are running on x86 or even a sequential consistent processors. We can see that we can first execute y equal to 1, then run the second thread. So we get the value b equal to 1 here, which writes the value x equal to 1. And then the second thread completes. It comes back to the thread 1, and it gets value both a and b equal to 1 as a weak memory behavior. So because of this compiler transformation, this behavior is also possible in x86 machines. So effectively, all the processors or the machines that we are using, this behavior can be possible to have. Now, considering these overall weak memory behaviors in the underlying compilers and the processors, the programming languages thought to come up with as a first-class primitives as a concurrency in the programming languages. So it was initially done by several threading libraries, but later it became a mainstream part of the programming languages. And the desired properties here, the programming languages wanted to have is first a platform-independent abstraction. So they wanted to propose a concurrency model which will work for different compilers and different architectures. The second property is good programming model. So this should be understandable to the programmers who are writing these programs. And third is supporting optimizations. So we will come into more details, but essentially we don't want to stop any compiler optimization, or we don't want to stop any hardware optimizations if we write a program in a certain form. Now, let's see that how concurrency can affect the program optimizations. So remember this earlier example, and consider that we are considering the model as sequential consistency. So in that case, what may happen, we have seen, is that in the original program, sequential consistency does not allow this outcome, but after this reordering, it is possible to see this outcome, which means a compiler, if it performs the read-write reordering, it can introduce a new behavior. And if we look at compiler correctness, this is not correct, because compilers has to be semantic preserving, and it should not introduce any new outcome. So in that case, we say that that sequential consistency does not allow this read-write reordering optimization. Okay? And not only this particular optimization, in sequential consistency, any kind of reordering will be deemed as incorrect, because there it is possible that there exists some program, it will introduce a new behavior, and there will be a bug. So given this situation, there is a research question here that can we define a concurrency model for the programming languages which can provide us both optimization and programmability. So optimization is for performance, programmability is for correctness. Okay? And if you look at this, this is what you get as an outcome in this area. So this is a paper for 2015 which says that despite decades of research, we do not have a good model of concurrency semantics for the programming languages. Okay? So we will see that why it is the case in the next steps. But if you have any questions, then we can discuss now and then proceed to the next steps. Okay? So let's see. So before defining a programming model or a concurrency semantics for the programming languages, we should understand that what is the goal we have for defining such a model. So we set some goals for programmability, efficiency, and feature coverage. So for programmability, we say that it should not create any bogus execution, or in terms of out of thin air executions. We will see what do I mean by that. And it says that it should provide some guarantees for well-synchronized programs. So what it means that suppose we are writing program with locks, and if we have all the shared accesses within the critical sections, then we should not have any complicated problems. Now for the efficiency, what we want is that we want to allow all desired compiler optimizations, which the mainstream compiler are today performing. And we want the efficient hardware mapping of the shared memory primitives from the languages to the architecture ones, okay? So that we don't compromise any performance. And at the same time, we want to handle all the concurrency features which are having in our programming languages. So with this goal, this problem has been addressed starting from quite early time. So The first model in this case, what to my knowledge, is data rest-free concurrency semantics, or DRF0, in 1990. This model actually came up with a very simple but very elegant solution. So it said that the program, if there is a race, then there is a problem. Okay? And what is a race? If there are concurrent accesses on the same memory location, and at least one of them is a write operation, then it is possible that this program can be buggy. So once we try to understand that how we can get rid of this, the model actually differentiates between two types of variables. One is a data variable, and another is a synchronization variable. Now, for example, if we go back to the earlier program, we can say that X is a data variable, which is kind of, you can think that it is like preparing data in a thread, and which information it wants to communicate to the other thread for computation. And the synchronization variables are kind of flag variables, which tries to signal the other thread that the data is ready, now you can consume it. Okay? Now, it says, the model says that race is unavoidable because we have to communicate, so there should be some accesses on the same memory location. But races on synchronization variable is all fine. We can have data races on those variables, but if we have races on the data variables, it will be an undefined behavior. Means there is no guarantee the semantics will provide for those particular executions. And now, if we look at this particular program, we can see that if y is a synchronization variable, it can be used to communicate this information without any data race on variable x. And based on this model, this has been a foundational model for the modern concurrency semantics for the programming languages. So this model was extended in Java to define a semantic model, and the first model in Java memory model came in 1996. But it was found that it is not agreeing to all the optimizations which are performed in the then JVM hotspot compiler. So the model in 2000, they found that the model is broken. And there were efforts to fix this model, and the second version of the model was proposed in 2005. But again, in 2008, it was found to be broken, because it was again not supporting some of the optimizations and guarantees what the programming language wanted to give. After that, there are several propositions to fix the model, which should give, the idea is that it should give, if you remember, all the semantic goals, the programmability, optimizations, and feature coverage, which was difficult to achieve. And so far, with the fundamental models, there is no solution to this particular idea. So in the concurrent world, people started thinking of defining, yes?
Quick question, are you assuming there is no update to synchronization variables, like they are read-only or what, in the previous example?
This example?
Yeah, what if y is being, or there are updates to synchronization variable as well?
Yeah.
Okay.
Yeah, there are update variables. Here I have gave the example, I simplified the example.
Yeah, in general, okay.
Yes.
Yeah.
So any more questions up to this example?
I see one, two
there. Yeah.
Could you go again the data variables, because I think y also acts as a data variable here, or
So it is up to you to define what is data variable, what is synchronization variable. So the programmer defines a set of data variables, a set of synchronization variables, and write the program.
Okay, that answers. Thanks.
Okay. Yeah.
So then the guarantee of race freedom is parametric on this choice of data variables and synchronization. Okay.
Yes. Okay.
Great, gone.
Okay. So it was found that along with Java, C++ also tried to come up with a concurrency model as a first-class primitive. So it defined a bunch of memory access with the memory operations. It defined that there are 4 types of memory operations we will perform in C++, which is read, write, atomic update, and fence operations. And they also defined a list of memory orders, which decides that the strength of these accesses for the synchronization. Okay? So, and then it started drafting this model, and then in 2008, the initial draft came in as the first concurrency model. And in 2011, the draft was finalized with several iterations, with the discussion with the researchers in semantic world. And it was finally, it was a mathematical formalization was released in the same year, in 2011. However, in 2013, people found that the C11 model is too weak, and it does not give the proper guarantees for well-synchronized program by any data race. It does not actually provide any data race freedom guarantees. And in 2015, we could show in a paper that there are many desired compiler optimizations are broken in the C++ concurrency model. Means that the model does not allow those optimizations to be deemed correct, which means that now it is not clear that which optimizations we can perform and which we cannot. Then there was a version was proposed to be fixed, and there were several propositions were actually there to solve this problem. 2 of them main propositions were in 2017. It was promising semantics and also RC11 in the same year. They were trying to solve 2 different kinds of problems, but they improved the semantic model significantly. In 2019, then we defined another concurrency semantics named weakest MO. The full form is weak event structure. And then there were consequently the more advanced model was proposed to solve this problem. Okay. Now, let me give you that what is the problem here. In C++, this model was actually considering this program and this execution. C++ looks at a program execution as a graph structure. And a graph has events which consist of memory operation, memory location, and value as an event to represent a shared memory access. And then there is some relations between these events, which are represented by edges. The program order represents the memory order, the order of the accesses in each thread, and read from actually combines a write and read operation together to show that how this read has read the value. And after this graph is constructed, it wants to see that if this outcome is possible, and it has some set of consistency constraint to check if this graph is correct. And C++ says that this graph is correct and this behavior is allowed, which we want. However, if you think of just a variation of the program in the first thread, also we say if A equal to 1, then Y equal to 1, along with the second thread. Now, this program should not have any outcome with both A and B equal to 1, because no hardware or compiler optimization can result in this behavior. But C++ says that this behavior is allowed for this particular program, and this behavior is possible. And this is where C++ model is actually being very weak for 2 reasons. It allows some behavior which is not possible in a program, which is termed as out of thin air behavior. And for the LBTEP program, there is no data race, but C++ says that there is a possibility of data race. Yes?
So just to clarify, it's not that we will get the behavior of A equals B equals 1, it's that this C++ analysis is going to lie to us and tell us that B equals B equals 1 is possible?
Yes, exactly. So the model is the weak one. And the deep problem is that once this is for one example, but in general, this does not give any guarantee. That's the main challenge. Now, what actually people notice that these kind of errors are happening because there is a cycle in this graph between the program order and read from edges, right? Now, next, there are some memory models like RC11, which actually said that such kind of cycles are not allowed. Now, what is the effect of it is that in this case, if we have to forbid this cycle, now we have to say that this behavior is also not possible in this first LB program, which earlier we wanted to be possible. Now, the implication is that now the compiler should not perform this read-write reordering. In the architecture level also, we have to stop it. For that, we can introduce some fences when we map this program to the architecture, or in the architecture level, we have to stop this pipelining and so on. So this problem has been solved in several other ways. I will not go to them for the interest of time, but there has been many challenges in this area which has been addressed in the model, and there are new properties which were actually came up, which the programming languages want today. And the C11 model has been expanded to many other languages, including the GPU programming, OpenCL, CUDA, and so on, where what we want is that to model the shared memory concurrency for the GPU programs, which is a new area. And here what we want that the threading model and the execution model is very different, but they also show the relaxed memory behaviors. And more specifically, in today, there are emerging heterogeneous architectures which have shared memory between the CPUs and GPUs. And the question is that what is the model of this kind of architecture and going to be for their programming languages? So quickly, if we just look at this particular architecture and this same program, suppose that we have a processor x86 and PTX are connected through shared memory, then for the CPU-GPU architecture, what will be the behavior if the threads are scheduled in different types of processors? So this is a question which I am investigating with some of my collaborators, which I find quite interesting. And basically, this raises several new research questions that how we can combine different memory models into one, what are the compositionality properties we can have, and what kind of separate compilation we can guarantee there. So to conclude, in this area, what I find most interesting and challenging is that it connects various concepts from PL, compilers, and architectures, and it has a very nice combination of theoretical problems with very much practical applications. So what I could not discuss in this topic is it's a diverse field with many important research which I could not talk about. I could not talk about the program correctness, compiler correctness. There are many work is going on. So if you are interested, we can discuss it after the talk or anytime I am here in this for this week. So feel free to talk to me. And with this, I conclude my talk. Thank you, and I will be happy to take any question.
Okay, we have time for 1 or 2 questions while Aslan sets up. Yeah.
So you talked about how to think about these models, and then you also talked about how people keep refining these models because they keep discovering bugs. But at the same time, one also has to sort of ground it with what the compiler actually implements. So how do we do that?
So basically, the compilers, when the models, basically we try to not to stop any compiler optimizations. The goal is that the optimizations which are written in the compiler, restricting them, first of all, is not desirable. Second, it is very buggy. So what we want to do is that allow these optimizations and then relax the model or change the model in such a way that the overall requirements are met.
But I come up with some model, and then it may not even reflect what the compiler is actually doing. How do we bridge this gap?
So in that case, first of all, that we try to prove the correctness of the compiler transformations. And if we find that it is not allowing this transformation, we have to either relax it or go back to the compiler and restrict those optimizations.
So it's like an iterative process.
It's an iterative process.
Oh, one more question there.
With regards to compiler optimization, you cannot move around instructions. But what if it's a non-concurrent program? Like, how does the compile, like in terms of what a compiler can view, it might not know that if it's a concurrent program or not. Like a function, like if you consider just a function call, so in that scope, it does not understand that it's a concurrent or not concurrent, and it might be called in a concurrent function. So in that aspect, why is it that such transformations are wrong, but they are correct in their its own scope, right, or its own semantics?
This is exactly what we want. The compiler need not to know the entire program. The compiler should know only on its scope, maybe at the function level, and it does not know what are the other codes are running in concurrent with this particular code. So the semantic model and the compiler correctness results, which we prove, considers that there exists any arbitrary context on which this transformation has to be correct.
Okay.
So that's how it is proved, and compiler should remain that way. It should not look at the entire.
Okay, thank you.
So that's a requirement.
Great. Let's thank Sham again.
Thank you.
Okay. Then the last talk of this session is by Aslan Askarov. Aslan is an associate professor at Aarhus University, and he's an expert in an area called language-based security. So who better can give a talk about how to read a PL security paper? Go for it, Aslan.
Thank you. Thank you, Marco. Is the sound okay? All right. Hello, everyone. So I want to talk about how to read PL security papers. If you're attending a conference like this, and also other conferences that are in the general area of programming languages, you will see that there are sessions dedicated to security, computer security. If you have just started working in the area of programming languages, you might have seen these textbooks. If you flip through the table of contents of his textbooks, there is no security in there. So how do you survive a session on computer security if you happen to be here? And there is also, so this is to help you. To help me, I submit papers to these conferences. And sometimes, once you get more and more mature, your advisors and your mentors will hand you over the papers to review. You may review my paper, so I want you to have the right mindset when reading my papers. All right. So today I want to equip you with a few questions that you should be asking yourself when you see a paper on computer security in the PL proceedings. These are the questions I use. It's generally a very broad topic, so the usual disclaimer is this is just perspective of one single person, okay? So if you look into a paper in the proceedings, so this is your typical anatomy, right? You will have an introduction over here, you'll have a conclusion, related work, sort of, here you'll get your, the meat and potatoes, the Greek letters and the graphs section of your paper. A PL security paper is more or less like this, with the key distinctions is you will see there something called a threat model, right? This is really important. And I cannot underemphasize how important it is, right? But rather than me telling you why this is important, let me bring in a quote by somebody else. This is a very nice write type from 2012 in CACM, so it's kind of accessible, by David Bazin and Srijan Kapkun, where they are reflecting on the research value of publishing attacks. And the highlighted sentence is the key. They say, what makes security special is the role of the adversary, right? Cue the threat model that I was talking about. A system security can only be evaluated with respect to a model of the adversary, that is description of their capabilities, right? There's one more quote that I really like from this paper, so let me share it with you. So just earlier they say, as our physical and digital worlds become more tightly coupled, the increase of attacks will increase as well as their consequences. You know this stuff, right? You just see it in the news. But this is really nice. They say, many of these attacks will be newsworthy, but most will not be research-worthy. So this brings another question. If you're reading a paper, where is the research worthiness of the result that's in the paper? Is it just yet another iteration of the bug that we have known for 40, 50 years, just in another system because people didn't do their homework? And then they conclude here, in our view, the most important reason for studying attacks is that they can help refine this model. OK, so the adversary. So what's the adversarial thinking? And the adversarial thinking is thinking about abstractions. As PL researchers, as computer scientists in general, as engineers, so to say, we are in the business of building abstractions, right? That's what we do. The adversary's goal is to think in between the abstractions. That's what they're thinking. So if this is your sort of like one way to display cake of the abstractions that we work with, this is a picture from a very nice write-up by Frank Peasons. So this looks familiar, right? Hardware description languages, processor, and so on and so forth. On top of this, we have high-level programming languages. PL is everywhere here, right? Even at the level of a hardware, there is a programming language, right? Let alone at the top level. We use programming languages to operate, to implement the systems. So it's obviously relevant that we see papers on programming languages and security. And you can enumerate a number of instances where there are issues. For instance, the classical ones are about the buffer overflows, where the attacker knows how the memory is laid out, but the programmer doesn't think about it. So the adversary is exploiting really the gap in the abstraction layers. The adversary thinks like this not just in the digital world. They also think about it like this, exploiting the gaps in the physical world. So let me give you just two different examples. So if you have a smartphone, you have a keyboard, you have a desk, you can use the smartphone accelerometer to infer keystrokes from the desk. So, so there's basically, as you type in your password, the accelerometer picks up what's going on, right? So again, really thinking in between abstraction layers. This is my favorite computer security paper, where somebody figured out that the DNA machines that are used out there for DNA sequencing, nobody cares about their computer security, because usually they're kind of like in a lab somewhere. But as a matter of fact, you can synthesize a biological substance that once it's actually being picked up by the DNA sequencer will trigger a sequence of events that will end up in a buffer overflow, right? So, and then it's pretty cute, right? So you can think about, like, this is really the way you can think as an adversary. So the threat model, right? What is really the threat model? The key question here is really simple. Who is the attacker? What can they do? For example, if you have this picture, where are they in this picture? Where are they on the stack, right? They can be across the network. They can be on the processor. They can be in the cloud with you, and so on and so forth. And all attackers are valid. What's important is that the paper at hand is actually, they know what attacker they have in mind, right? So you have to be aware of it. And sometimes it's meaningful to compare different strengths of the adversary, right? You can say that, oh, I have an attacker who only observes inputs and outputs, and then I have my work focused on this attacker. Good, right? We're clear about the rules of the game. We're defining the rules of the game. So the threat model is really like, what are the rules? Sometimes you can have someone who's stronger. They will not only just observe the I/O, they will also observe all the concurrent concurrent writes into the memory. For example, if they are running in a parallel process, or they may have so much access to the machine that they can look into the timing of the events, right? And this relevance of different threat models, it evolves over time in the literature, right? So timing attacks are really focused right now. There's a lot of work, but it's not like community didn't know about them. They've known about them for 20, 30 years. It's just they were not relevant, because in order to perform a timing attack, you would assume that the adversary would have to have physical proximity to the device. These days, they may just be on the cloud, sharing the same data center rack with you. So that gives them that possibility. So suddenly an attack that considered to be kind of, you need to have a lot of privilege to exploit it, is becoming something that can be done at scale, right? Once these things can be done at scale, they become relevant. Another example is attacker knowing the source of a program versus providing the program that's going to be executed. And before the browsers, people didn't necessarily take seriously the fact that we can run adversarial code. But we do it all the time in the browser, right? The code comes that's executed from God knows where, right? So it becomes relevant. So the question number one, when I read a paper that's about programming languages is security is the threat model any good? Do the people writing the paper know what their threat model is? I hope they do, right? And the nice thing about asking this question is it's the threat model that keeps us grounded, right? And they come in all forms, but I think it's important. It's okay if the attacker model, if the threat model is relatively weak, right? So they may assume that, we're just only focusing on the issues where the program at hand is not something that's given to us by someone who is really malicious, but we're just trying to fix incompetence in programmers working, right? That's okay, right? So we can consider a relatively weak threat model, but then the paper better than compensate for it. Maybe they can perform some kind of a static analysis that will target real code, right, for this kind of a threat model. So this is the security folk theorem. I don't really have a citation for it. I just talked to some bunch of colleagues and asked them, does this make sense? And he said, yeah. So in between security, expressivity, and performance, usually you get to choose 2 out of 3, right? And the threat model here kind of helps, right? So you can have relatively good expressivity with relatively good performance, and people doing optimizations already there might start doubt me, but usually security is something that's compromised, right? On the other hand, you can have good performance, good security, but you can't really program anything if you have that system because then it's going to be extremely restrictive. Okay, make sense? If you have any questions, please shout, right? So that we can make it. Yes?
So I'm a little confused about what a weak attacker means. Is a weak attacker someone? So is a weak attacker someone that does not have a lot of knowledge and then attacks like that? Or is a weak attacker an attacker that can't do a lot of damage?
Right. So a weak attacker, let me give an example. Between an attacker who knows what program you're running, who doesn't know what program you're running, and who has given you the program, the one who has given you the program is the strongest.
Okay.
Right? The one who doesn't know what program you're running is the weakest.
Okay. Perfect.
Right? Make sense?
Yes.
How can we have security and performance together? My assumption is if we have security checks, we need to give up on the
We
performance.
reject most programs because then we sacrifice expressivity.
So we sacrifice
expressivity. So I will give you, let me give you, so I can tell you, yes, here is a little programming, domain-specific programming language. You can implement, a few algorithms in it, but not much more than that, right? So it's going to be extremely restrictive. A good example of that is the literature on implementing cryptographic primitives. So in the literature on cryptographic primitives, there's a survey in cryptographically aided cryptography. I don't have a quote on it here, but it's like 150 citations, I think, in that paper. Marco might know. The research questions they're asking is, how can we use a low-level programming language, such as assembly or C, to implement cryptographic primitives, such as RSA, and so on and so forth? So they come up with kind of static analysis, restrictions, domain-specific languages, the whole garden variety of everything people talk about here, to target that concrete problem. The programming languages and static analysis they come up with is extremely restrictive. You cannot have an arbitrarily looping construction in that language, right? Because they say, we're implementing crypto, loops have to terminate. Boom, right? So that is an example of then restricted expressivity.
Okay, thanks.
Okay, but you get a relatively high security guarantee because we're talking about cryptographically bounded attackers, so on and so forth. Okay? Good, let's go on. All right. There are subtleties in threat models, right? So pay attention. So usually we will say that security against a strong adversary implies security against a weaker one. Earlier to your question, I gave you an example. Well, if I can show you that my system is secure against an adversary who has given me the code, that's the strongest one, then it's probably going to be also secure against the adversary who has less capabilities. They don't know what I'm running, right? So that kind of common sense. There are caveats, right? There are subtleties. So pay attention. There's a three-liner here. Three-liner, and I have two users. I have A and B. A is the manager. B is the employee. So at the moment of executing the first line of code, manager can know everything professional about their employee. So if I have a line that says, send to A what B's salary is, that's A-okay, right? They have access. It's okay to let them know. Now it's time for A to retire. They are no longer the manager. We are doing the same operation yet again after A has retired. Now we're asking ourselves the question, well, this was okay, fine. What about this one? Is this okay or not? Some of you will say, no, it's not okay because A is no longer the manager, right? They have no business learning this information. Somebody else say, well, that's a very operational way of looking at things. Let's think about what does A actually learn from knowing this, right? So if I knew that, you know, my employee's salary was $100 yesterday, nothing's changed, just by sending this again, I'm not learning anything new. I knew this, right? So you can play it both ways. But the difference here is I am in this case, this is okay if we assume that we have an attacker who can remember everything they have seen. If you have, on the other hand, an attacker who starts forgetting things, who by common sense will also be an attacker who is relatively weaker, then this is actually not okay. So we have this little subtle thing that suddenly this little three-liner is okay for a strong attacker, the one who keeps remembering, but not okay for an attacker who is forgetting stuff, right? So there are subtleties. Pay attention to these subtleties. They usually arise when there is some kind of dynamicism in the system. There's dynamicism here because the security specification has changed halfway through. A has retired, right? It's not a static policy. Yes?
Also, guys, like, what if, like, A's salary has changed in between? Sorry, B's salary.
Yes, that's also a valid question. But assume it did not change, right? Assume we know that the salary changes at the first of the month, right? And we're between 15th and 16th, right? For the sake of example. But yeah, you're perfectly right. Make sense? Shall we go on? OK. So this was about threat models. So asking the question about what's a threat model is the first technical thing that I want you to keep in mind when you're reading the papers. The second thing that I do is I use this Lampson's notions of elements of security, right? I think it predates Lampson. I've seen this given. He gave a lecture at Maktobedorf a while ago. So it's really these three components. It's about policies, mechanisms, and assurance. And if you're coming to this from a programming languages background, it's specification, it's implementation, and it's soundness, right? So these are the same things. I like to point them in this kind of a diagram. So you have a policy, and the policy is what is the meaning of the security in the first place? That is a very, very, very much a high-level question. The things I expect to see here is confidentiality, preserve the secret, is integrity, preserve the integrity of the system, availability, and so on. These are high-level conceptual notions. The less technical they are, the better, because it's about what is it we want. All the technical complications are in the mechanisms and the assurance. So in the assurance. Here we'll have your types, your monitors, your static analysis, program verification, fancy runtime systems, and so on. And in the assurance, you will have very complicated proof engineering, right? That's where it is. So this is how we link together. If you haven't seen this, it's very easy to conflate policy and the mechanism. A good example of that is, for example, people sometimes conflate good cryptography with a policy, right? It's a good engineering to do good cryptography. But cryptography is a mechanism to give you the confidentiality. Policy is the confidentiality, right? So keep that in mind. Focus on what's at stake here. OK. So then the question is, question number 2 when I read the PL security paper, is what are the policy mechanism assurance elements? And the question 0 is, does the paper even have a definition of security, right? Do the authors of this paper even understand what they mean by security in this case? Sometimes they don't. Sometimes they say security is just this should not happen, that should not happen, and this should not happen. So that puts it in a bit of an ad hoc situation, right? So these are just things that are not supposed to happen. You don't really have a positive definition of security. doesn't mean the paper is bad. There may be other good things about the paper, or it means that the security question at hand is really complicated. So complicated that the state of the art has not yet reached the point where these notions have yet been given a good formal definition, right? That's a symptom of something that is not there. If there is a good security definition, then the next question to ask is, what kind of property is it, right? Things I like in the security policy, I like the security policy that is semantic. For instance, if I'm asking the conceptual question, given a piece of code, is this code secure or not? That should not depend on, is there dead code in the source program or not? Make sense? Right? So it should be really semantic, right? It's nice to have a security definition that's focused on on the threat model. It's attacker-centric. And I also like the security definitions to be conceptually shallow. Now, you don't really relate conceptual shallowness with goodness, but a good security definition is something that you can explain to your family member who doesn't know anything about computer security, right? So, and then, again, keep all the complications in the mechanisms and in the assurance, right? We have time for an example. Yes, I think we have time for an example. So I'll give you a little programming language that you will see in the textbook, right? Your classical imperative programming language. And I'll give you 3 different example policies. And the first one will be, well, if I have this programming language, the interesting things about this programming language, so this is just the while that you've seen, I hope you've seen before. And I have primitives for input and output over a channel, and I can have a channel that's secret and public. OK? Right? That's it. And I can have different kind of security policies here. I can say there shouldn't be any public output after secret inputs. How do I think about this? Well, I can think about, well, if this is my trace, this is my output on the public channel, then there is a secret input. And after this, there shouldn't be anything blue over here. Right? That's how I'm thinking about it. You can think about outputs to public channel must be copied to secret channel, right? This is something a little subtler, right? So you can see, well, OK, there's an output here. There must be a bunch of events. But in the end, there's got to be a copy of the same thing, right? So this is, like, you can see, well, the first one looks like a safety property. This one is, the middle one looks like a form of a liveness property, right? So we're starting to make things a little more complicated. This last one says about public output should not depend on the secret input. This is something I cannot express, even formally, I cannot express as a property that takes only one trace into account. I have to reason about all possible traces, right? And this is, so when I say that all possible traces, for all possible traces, this is how I would encode my predicate on the all possible executions, right? This is something that you may have seen in the literature as hyperproperties. OK, that was number 2. The third way I'm looking into the paper, I'm evaluating it using this classical design principles from Salzer and Schroeder. This is one of my favorite papers. It's from 1975. I read this paper every year because I teach a course on this stuff, and we look into these things. And one of the things they do is they come up with a bunch of design principles that one should adhere to when building a secure systems. And these are, a lot of them are common sense, but it's kind of remarkable how much they've gotten right more or less 50 years ago, right? Economy of mechanism, your system should be simple because it's easy to verify. If you ever fire to prove assistant, you will appreciate the simplicity of things you need to prove, right? So obviously, fail-safe defaults do not give access by default. Makes sense. Complete mediation, do not trade performance for security, makes sense. Open design, no security for obscurity, also makes sense. Separation of privilege. This one escaped me until like half a year ago. I was like thinking, what the hell is this? Can I come up with a good modern example of a separation of privilege? The one they give in the paper is about, well, if you have a system that launches rockets, you need 2 high-level generals, each with their key, to sort of fire up the missile, right? So then if one of the general's key is compromised, then you still don't have rockets in the sky, right? So you separate the privilege to perform a security-sensitive operation. And then it dawned on me, the most modern incarnation of that is what you will call a multi-factor authentication, right? Where you have to know your password and you have to have a device. It's actually sort of like, it's kind of fascinating that it has this new modern reincarnation. Least privilege, need to know, you may have seen this. Least common mechanism turns out to be incredibly powerful. And then they talk about psychological acceptability, that the passwords are not a good idea in 1975. So please go read that paper. But I want to emphasize why it's important is because, why do I like these principles, is if you have if you exercised and thought about these ideas quite a bit, you realize there's very little new in computer security. Because these principles really, really help you think about the same phenomenon appearing at different levels in your system, right? For example, there's a principle called least common mechanism that says one should minimize the amount of mechanism that's common by more than one user and dependent on by all users, right? Every shared mechanism, especially one involving shared variables, represents a potential information path between users and must be designed with great care. Further, any mechanism serving all users must be certified to the satisfaction of every user. So this is really cool because this is a principle that keeps on giving. You can design a program analysis that will tell you, well, there's got to be separation that needs to be enforced, or you can design a program analysis that will tell you, well, we're going to allow sharing of resources, but we will prove that that sharing of resources is actually sound, right? And the idea that if you have something that is common in your stack and that creates a security issue, I mean, that is something that's common for a processor cache, for a disk that shares the vibrations. So it's the same principle that can be exercised across many, many, many layers over. OK. How much time do I have? 1 minute. OK, good. I'll skip some examples. I'll tell you one thing. So privacy. You will see privacy a lot. And my recent revelation is I don't think I understand privacy. I've been doing work in this area for almost. Security and privacy is bundled together. People kind of acknowledge that they are related but not the same. And the more I think about it, the more I realize I don't know anything about privacy. If you read if you know people working in other areas of CS, they will know, well, in information systems, there's a notion of privacy that's about contextual integrity. I have more time? Yeah. OK. In theory, there's a notion of differential privacy, right? So you can go as far as 1890 to the paper by Warren and Brandeis. It's one of my favorite papers as of lately. It has nothing to do with computer science, but has a lot to do with privacy. And what they do here is they talk about the privacy as the right to be let alone. I encourage you to go and read this paper because it's just an amazing example of no bullshit writing, you know? So they will, and how far ahead of time it's been. For instance, they say instantaneous photographs on newspaper enterprises have invaded the sacred precincts of private and domestic life. Numerous mechanical devices threaten to make good the prediction that what is whispered in the closet shall be proclaimed from the housetops. I find this very relevant to today, right? And this is a long time ago. And then they kind of predict fake news. They talk about the fact that even gossip apparently harmless when widely and persistently circulated is potent for evil. And my favorite line, it both belittles and perverts, right? Can you write a PLDI paper in which you will, I dare you to write a PLDI paper where you will have it both belittles and perverts. Related to the, why don't I understand privacy? So I told you about this idea of the least common mechanism being a sound way of thinking about the systems that basically, you know, if you, the less sharing there is, the better you are, right? That's kind of the general idea, one way of interpreting that. Well, comes this cute cat theory of censorship. This is by Ethan Zuckerman. The paper is from 13. I've seen it's been also quoted from 08. And what this cute cat theory of censorship says is that if there is a platform, think of a Facebook and Twitter, so on. And if this is a general purpose platform that's used by people, it's harder to censor it. It's harder to shut it down because people like their cute cats. But that's a platform that can be used for the activism. So if you think about privacy more generally, not just from the perspective of what you see in some of the theory conferences, right? But what is it actually privacy for people? And censorship resilience is one of the aspects of it, right? Then suddenly the thinking principle of designing a system is a challenge because this is really very much the opposite of what the least common principle tells you, that you should have a separate system for private conversation and a separate system for cute cats, right? So this is why I think it's kind of nice to think about these things. Do I have a time for more? Yes. OK. I'll show you one more technical thing. So you have to be careful about the details, right? So I showed you this least common mechanism. So, and the idea is that as we are implementing systems, we sort of need to be aware of these subtleties. So let me share you a subtlety. So in my group, we have a homegrown little programming language that we call Troop. And the idea is that we basically use it as a research lab to play with different ideas. You don't need to know a lot, but I'll just give you this example. Technical, but stay with me. So what you see here is 3 different processes. So we've got the left one over here. This one has access to the secret. We have a middle one, does not have access to the secret. And then we have the rightmost one. That one doesn't have access to the secret. So we have a parallel composition of 3 processes. OK? What happens here is that we branch on the secret, then we're doing something that's going to take 100 units of time, doesn't matter what. Here we will take 20 units of time, doesn't matter what. Over here, we have just a straight line code. It's going to take 50 units of time. And then we'll perform a side effect. The side effect will consist of writing 1 on the public channel. And here we have just the side effect of writing 0 on the public channel. OK? So I'm going to tell you, if you consider implementing a scheduler that's actually going to be implementing this abstraction, right? And the scheduler is round robin. This is A-OK. I implemented the scheduler, right? The first thing, it was A-OK. But even for a toy language, we itch to add performance, right? So what do you think is the first way to add performance to something like this? You have an idea? Will we add performance? No. Anyone else? Say again? Caching. OK, so I'll tell you. So what you do is you batch. So instead of sort of interrupting the execution at each instruction, you let each of the processes to run for a little longer, right? And then you make the context switching coarser, right? And that gives you better cache locality, for example, right? Because there's fewer context switching. So that's like the first textbook implementation of making things a little faster when it comes to these things. OK, so I implemented it. And I have chosen sort of a countdown. So this is n steps per thread. And for this example, let's set it at 60. OK, so what's going to happen is with each instruction, I'm going to decrease the counter. So it's 60, 59. When it reaches the 0, we context switch. All right? And so on and so forth. So let's do this. So if I start with 60, I'm going to be executing this process. I will run out of my counter. So I will be here somewhere, for instance. So if this takes 1, this will take, what, 59. So there will be still 59 instructions. So we will set the counter to 0, right? We will context switch over here. It will be 60 again. This is 51, right? So we will make the public right. We will context switch over here, and then we will make the second public right. So the order of these 2 sends will be 1, 0. OK? With me? Now, let's suppose that we're executing this again, but now we are in a situation where this is a false branch. So I'm going to come over here. So this is 1. This is 20. So, and I'm done. What's my counter at? 60 minus 21, 39? Yes. My bug was that I did not reset the counter. So it's 39. We're out of things to execute. We're context switching with 39. We will not get to the send, right? The counter will go to 0 in the middle of the skip, right? So then the counter reaches to 0 before reaching the send. The context switch, we do this first, and then we're coming back here, we're doing the second. So that little bug of me forgetting to reset my counter leads to the fact that now the order of the side effects is 0, 1, right? What functional specification would catch that bug? None. You need security specification for these things, right? I didn't know, the only reason I knew about this attack because we kind of predicted that this is something that can happen. And then I did property-based testing of my implementation to see is it actually possible. And I was really surprised that I had my own bug in my own code. OK, my chair is signaling that I should wrap up. And I think I'm ready to wrap up. So I shared with you the thinking process I have when reading a PL security paper. This is just the summary of these things. You have to remember what the threat model is. Keep the security policy mechanism assurance triangle in check. That really helps you to position the paper. And appreciate that a lot of the PL techniques are in the mechanisms and in the proof techniques, right? And then think if you can relate what the paper is doing at a high level to this 75 paper from the 75 on by Salzer and Schroeder on the design principles. And these questions are there to assist your core expertise, right? So whatever it is your core expertise, that will be, an extra booster to make your way through the paper. If you are a PL generalist, you don't care about security, I think there is a lot of value in reading these papers because, again, security by itself is an incredibly pragmatic discipline, right? The discussion about threat models is there to tell you that even though these papers may be theoretical, they are really grounded in practice, right? So it gives you touch with realism, if you will. And if you are expert in something, chances are your expertise will be relevant. If you're expert in program analysis, you might have an application, and so on and so forth. Garbage collection, proof engineering. Chances are there will be applications for your core expertise in security. A slide with a few reading takeaways. These are sort of like survey classic papers, but I want to summarize. Remember that security is about the whole stack. Programming languages are part of implementing the stack, a part of a stack, and I think we will see more of PL security papers in our proceedings. Thank you.
Do we have one quick question?
So, thank you for the talk. My question is that when we consider these different threat models, and what I wonder when I read a paper, that a solution for a threat model, whether it introduces another security, possibility of another security violations or not. Is it something possible?
So let me see if I understand. So the question is, are we introducing insecurities by trying to focus on the security? I can't say it's impossible, right? I can't think of an example from the top of my head, but I wouldn't say it's impossible, right? So because, for example, I don't know, you might make it easier for a stronger attacker to do something, but if that's an attacker that's out of the scope of the paper, that might be sort of technically within the rules that they set up for themselves. Right.
Thanks.
Other questions?
We had questions during the talk. That's OK.
That's fine.
That's fine.
Then let's thank Aslan again. Now what's going to happen is that we have, PLMW mentoring lunch. So that's downstairs at the Fellini restaurant. You have to check there are like tables with this PLMW signpost, like sit at one of those and find people that have this like mentor badge. And yeah, like just enjoy lunch and some mentoring discussion. See you at the section. Oh, and there are also 2 tables for Apple, like dedicated to Apple. So if you're interested to talking with those folks, sit at those tables. We will resume with the program after lunch at 1:40. So see you later at 1:40 here.
Cool. And next up, we have Max, who is a new professor at the University of California, Berkeley. He works on eGraphs and was one of the co-organizers of the eGraphs workshop that happened yesterday. Can we make him? And I was going to say something. Oh, so if you don't know what eGraphs are yet, that's totally fine. They're a very old technique kind of made new again by Max and others. He'll be talking about that, I'm sure, as part of this talk. And as a kind of fun fact, the first paper of my PhD actually built on a framework that Max released as part of his earlier PhD. So the first paper that I wrote was actually kind of related to this stuff. And Max will be generally talking about optimization and kind of a grand tour of what optimization in PL looks like. Maybe.
It was working? Okay, sorry. I jumped the gun. Cool it.
Let's try this one more time.
Pick a different one. I've got 4.
And ooh, do a 4.
Try this one. I don't know.
Can you check your display settings?
I mean, there's. Yeah. Oh. Do you see anything?
So you're not seeing one?
No.
Do you not have an HDMI port?
No, I don't have an HDMI port. I mean,
Can you just leave it?
Let's try this one. Oh. Yeah, this one's working.
There we go.
Good enough.
Also, before you start, can you take off your
I'm tethered in.
It's a topology puzzle.
All right, now we're ready to go. Thanks for having me. I'm excited to talk about program optimization, a sort of unbelievably broad and deep topic. So I have 28 minutes now. So this is going to be a whirlwind tour, and I'm going to try to give a little, like a light taxonomy of at least some parts of this cool field that I'm finding interesting. And each part of this taxonomy, there's already been entire theses and careers sunk into. But that's okay. One of the things that I want to get across is that the PhD is obviously about depth, but breadth is cool too. And by finding buddies who know about these things and asking them what papers to read, I've had a lot of fun sort of dipping my toes into some of these areas of other areas of PL, and we'll even get into a little bit of non-PL stuff about optimization. So let's get started. What's a compiler? Well, for the purposes of this talk, you're probably familiar with what a compiler is, but a compiler is anything that takes an input and produces an output, right? And in particular, we're concerned about constraining that output to have some relationship to the input. For a lot of purposes, for most purposes in this talk, that predicate might be equivalence, some sort of symmetric relationship, but it could be anything else. Maybe it needs to be lowered into some other fragment of the language or whatever it may be. And when we talk about an optimizing compiler, right, our job is a little bit harder. Right? We're now adding this notion of cost, as a property of the output, and now we're sort of doing an argmin, right? We want to consider all of the possible outs that are related to our input and find the one whose cost is minimized. And it's worth noting that when programming languages, when we talk about compiler optimization, program optimization, we typically mean minimized-ish, right? And this is interesting because when you use the term optimization in a lot of other areas of computer science or mathematics, they really mean optimization, right? They mean like if it's not the optimal thing, it's incorrect as an answer. And that's not typically what we mean. So we'll settle for minimized-ish. Okay, so you may have seen a picture that looks something like this when talking about like how to optimize a thing. So in sort of very vague terms. So we're writing a compiler, and this is our input, some point in this big cloud.
All right, and this cloud is the space that defines all of the other programs that are related to our input in the correct way. Maybe it's, like I said, equivalence. These are all the equivalent programs, perhaps. And I've helpfully organized our cloud from left to right, where the better programs may be faster, maybe we're optimizing for code size, or whatever the metric may be, are to the right. So the conventional and predominant and most effective and most used way that we're going to see, and we're going to talk about this more in detail later, to optimize these programs is basically about baby steps. Right? We're going to use transformations iteratively, typically phrased as rewrite rules, to sort of iteratively change one program to the next, to the next, to the next, hopefully moving to the right along the way. Crucially, all of these steps stay within this cloud, right? Each of these steps is designed in such a way that it preserves whatever the property that we care about is, okay? And if they all go to the right and you do it until you can't do it anymore, then you've wound up to the right of where you started and you've optimized your program. Note that we may have hoped to sort of end up in this corner, which is, I guess, slightly better, but we wound up in this corner. And in this situation, there's nothing we could have done about that because we sort of did it greedily. Another way to wind up with an optimal program is to not do it iteratively starting from the program, but sort of starting from scratch. So you notice how I've changed the text up here from optimizing a program to building an optimal program. And this is a little bit of a different paradigm. One way to think about it is you're sort of approaching our cloud of acceptable programs from the side, right? So we're starting with programs that may not have the property that we are, or at least they might not in and of themselves have the property that we care about just yet. But we can start by building up some small set of programs, and then we can compose them with one another, right? And this is a key distinction that I want to make, is when we are within this cloud, our sort of step in our search for an optimal program was transforming one program into another. And here our step is going to be composing programs with one another, enlarging this space until hopefully it intersects with our space of acceptable programs, all right? And this is going to be the sort of two approaches, the two schools of thought that I'm going to break down a little bit in this talk and give some examples for. The first I'm going to call transformation. And this is where we start with an acceptable program. Typically, it has the property that we care about, or it's close to it. And we build towards the good, right? We take baby steps, and those steps look like transforming an expression, transforming a term, typically with something that looks like a rewrite. The key questions we have to ask ourselves when we're designing an optimizer in this way is, well, what step are we going to take, right? At any given moment, we might be able to rewrite this plus to a times, or turn this division into a shift, or do something entirely different. And we might be able to do any of these things at many points in our program. Maybe it's a big program with a lot of additions in it. So which step do we take? Which one's going to get us to the optimal program, or even a better program? Likewise, you notice I'm sort of using the language of search here. We need to think about how do we manage our state space, right? You can sort of imagine about searching for an optimal program as sort of traversing a big graph where, one node is where you start, and if you take a transformation, you're sort of, taking an edge to another node. And this graph, in many cases is going to be infinite. So are we just going to sort of keep track of one node at a time, or going to, maybe you've written, Dijkstra's or A star or something where you keep track of a heap of something of the nodes that you want to explore from, something like that. And then the other paradigm that we're going to talk about a little bit today is called synthesis. Now, I call it synthesis to sort of evoke program synthesis, and indeed, I think, enumerative program synthesis, which you may be familiar with, is definitely within this school, but I want to take a broader notion of synthesis and really be thinking about any paradigm in which our baby step is composition rather than transformation, okay? So one way to characterize this set is you build up good programs and you try to find an acceptable one, right? I think our picture did a better job than this, where we're sort of approaching acceptable programs starting from the good programs. Like I said, a key distinction here is that instead of transforming terms, we're composing terms. And this can be either bottom up or top down, right? If I'm trying to build a term, I might start from the bottom, start with my leaves like constants and variables, and then use connectives to build bigger terms. Or I might decide that, like, for whatever reason, the optimal program that I'm the program that I want is a plus. Well, a plus of what? This is sort of top-down synthesis. I have plus with holes in it, and then I'll do some process to sort of iteratively figure out what I'm going to put in those holes. Likewise, we still have questions to answer, right? Which, this is sort of this sort of process, because we're composing terms, is sort of defined by our grammar, right? We're considering at every step, which term are we going to construct, right? Like, how are we going to come up with the next sort of problem, the next term that we're going to be considering. And likewise, this also has the same state space management sort of questions. Are we going to be holding on to one program at a time, or a small set, or all of the possible programs in sort of an exhaustive synthesis? These are all sorts of questions that we need to ask. And again, I've used this sort of phraseologies to sort of evoke search, or sort of combinatorial optimization, basically graph search, if you're familiar with those sort of techniques. Because I think that while can be very expensive in a lot of in general settings, it's a useful perspective to think about program optimization. All right, so as part of our Whirlwind tour, we're going to make it through sort of 4, I'm calling these algorithms, but they're sort of ways of approaching program optimization. On the transformation side of things, we're going to talk about sort of classical term rewriting. And again, this is a huge, gigantic field, so I'm only going to sort of skim over the surface of it. And we're also going to talk about equality saturation, which is closer to a lot of the things that I work on, which is also, I think, on the transformation side. And then on the synthesis side, I want to talk about an instruction selection algorithm. You may have seen this in compiler's class if you've taken that. And then we're also going to talk about query compilation. And query compilation, I mean SQL query compilation. So this is something a little bit outside of programming languages, but I think it's got optimization right in the name, right? It's got to be program optimization. And it has a very similar flavor, right? Like they have cost functions. They're trying to make the code go burr, right? Like these are the same kind of things that we want to do when we're building and optimizing the compiler. So I think it's a great source of inspiration. And while I think that term rewriting fits solidly in the sort of the canonical transformation sort of approach, and I think instruction selection, as we'll see, fits squarely into this synthesis school of thoughts. These other 2 algorithms, quality saturation and query optimization, have a little bit of flavor of both. And I think that's one of the big takeaways that I want you to take away from this talk, is that this is not a strict dichotomy, and both the sort of transformative approach and the more compositional approach can definitely work together. All right, well, let's start with term rewriting, and we'll have to go a little bit faster, I think. So here's just an example rewrite to get a little bit of notation out of the way. If you've never seen something like this, we have a left-hand side and a right-hand side, and when we're doing this, we're going to look for instances of the left-hand side. All right, and so I'm using these lowercase x as a placeholder. So if I see anywhere in my program an addition, an add, where it's adding 2 of the same things, I can replace it with, well, a multiplication of that thing times 2. Okay, and maybe I want to rewrite that in the other way, but for now we're going to go this way. And so how do you do this sort of term rewriting? Well, if I want to apply some sort of rewrite that looks like the left-hand side to the right-hand side, if I want to apply it to a term t, well, I'm going to search for the left-hand side in t, and that yields a substitution, right? And this substitution is going to map the variables in the left-hand side to subterms of the term that I'm searching it in, of t. And then I apply that substitution to the right-hand side, filling in these holes, these named holes, with the subterms of t from the substitution. And then that's my that's my transform term. As I've phrased it here, we're sort of only doing term rewriting at the very top level, but you can also apply this to the subterms as well. Okay, so term rewriting, as I've sort of phrased it, is definitely the dominant form of program optimization. Like my web browser on my computer, on my operating system, we're all compiled by compilers that are predominantly using this form of program optimization. Peephole optimization, sort of going from one term to a slightly better term over and over and over until you can't anymore. All right, and there's a couple of reasons why this, in my opinion, this is such a great way to approach program optimization. Not the least of which, what I didn't write down, it can be made extremely fast, right? Your state space can be constant. You're only looking at one program at a time, and you take these rewrites, and there's all sorts of fancy algorithms to very quickly do this search part, and just make your program faster and faster and faster and faster. It's also modular and composable. Right? So these rewrites are typically, sort of objects outside the system, and you have a rewriting system that can accept any number of these things and apply them in sequence. And so if you have a bunch of rewrites and you want to add a bunch of more rewrites, you don't really have to change your system. And they're composable in the sense that if you typically want to prove about each rewrite that it preserves whatever the property that you care about from the left-hand side to the right-hand side. So if we care about equivalence, we want to show that, hey, if I ever apply this rewrite to a term, it's going to be equivalent to the thing that I started with, right? And inductively, no matter how many times I applied, no matter how many rewrites, I'm going to stay equivalent. I'm going to keep preserving my property. So that modularity and that composability are really great, and I think this is why this technique is so dominant. Outside of optimization, it's also used in theorem proving to solve something called the word problem. And if you're not familiar with that, it basically means, given some rewrites, can you get from some term t to some other term t prime? Okay, and that's undecidable. So what do we do? How do we actually approach this problem? Because your Z3s and all these other theorem provers, and in fact, inside your compiler, they're solving versions of this word problem all the time. So how do they approach that? Well, the way that ideally you would like to approach term rewriting is by avoiding search at all costs, right? Like as we've been phrasing it, you have these questions like, oh, I have this term and I can maybe rewrite it in all these different ways and take me to some other node in my optimization graph, and then from there go to another one, and that's an infinite graph. So it's no wonder that this is a super impossibly undecidable. But there are two key properties that if you can show this about your rewriting system, this lets you avoid search basically entirely, or rather reduce optimization to sort of a degenerate search problem where you just go straight ahead. There's no decisions to make. All right, what are those properties? The first one is termination, obviously sort of desirable. And basically what this is saying is that that optimization graph that I was talking about, that rewriting relation, there's no cycles in it, okay? And the typical way that you prove this, and this is going to smell a little bit like optimization actually, is that you show that if you can rewrite from t to t prime, then some cost, you make up some cost function, it can be whatever you want, it could be AST size, number of pluses, it can be something more complicated than this, goes down, right? And as long as it's going down, and it eventually, would hit 0, more or less what this means is then you can't have cycles in your rewrite graph, right? Because you're always going monotonically down, okay? And this is intuitively, I think, useful for optimization, right? Like if you're putting a bunch of rewrites into your p-pol optimizer inside of your LLVM or your GCC, you want to make sure that at least most of them are making your program better. Yeah, you can definitely imagine situations where you sort of want to climb the mountain to find a deeper valley on the next side, right? But then you have to sort of start thinking about search again, right? And the whole point is we're trying to avoid doing that. Another useful property is that of confluence, okay? And confluence is the property where basically if you hit a fork in the road, if you can rewrite from t to t1 and t to t2, it doesn't matter which one you take, okay? Then that means that t1 to t2 will eventually rejoin in some other node later on in the graph. And together, these two properties allow you to sort of plow straight forward and not really think about, consider the choice of, oh, when do I apply which rewrite? It doesn't really matter. You're always going to, 1, stop rewriting, and 2, arrive in the same place. Like I said, your choice doesn't matter. But it's worth noting that you can still build useful things without these. We've been talking, I've been mentioning the sort of optimizers within LLVM and GCC and all these things. And in most cases, these properties have not been proven for those rewriting systems. They're probably pretty close, but these can also be sort of, manually enforced. If you are worried if your terminating system might not terminate, well, stop early. Just don't rewrite forever. If you're worried that your terminating system might not be confluence and you want to make it deterministic, well, just set explicit priorities. Say, we're going to do this rewriting system first, or this rewrite before this rewrite before this rewrite. You might, a different priority system might end you up at a different place, but at least you have determinism back. Okay? So you could still build useful systems without these things. But if we can get them, we would love to. Okay, now to switch gears very quickly, we're going to move on to instruction selection. So we're moving on to the synthesis side of things to give a sort of canonical example of what these compositional algorithms can look like. So this is another problem from the compiler's literature. The problem, succinctly stated, is basically how we have an AST that represents our program, and we're sort of at the last step of our IR. We want to lower from our tree-based structure to typically a list-based machine instructions. Okay? And the other input, aside from obviously our program, is templates that tell you these possible lowerings. Okay? What do these templates look like? Well, you have some simple ones that don't do really anything exciting. If you see an add node in your AST, you could probably somehow emit an add instruction in your instruction set. Most have an addition instruction. But a lot of instruction sets have fancier instructions that do sort of many operations at the same time that ideally you would use because they could be faster, right? So in this example, if you see in your AST a store whose pointer is the addition of a pointer by the multiplication of 4 of some other thing, which this could easily be an array access or something, then we can, if you're familiar with x86 or something like that, you can get all of this from a single instruction that looks like this. Okay, so we would love to use these things when possible, but we can also use the simpler instructions when needed. Okay? How do we cover the AST with these templates? It's easier to see this pictorially. We have our AST over here, and we have our funny-looking templates over here. And the point is to literally cover the tree with these shapes, each one representing a template on how to lower that fraction of the AST into some linear ordering. And as you can imagine, you could approach this as a search problem. Well, let's just pick one and apply it somewhere. Let's apply the biggest one. We're going to sort of approach this greedily. If we take our biggest shape and apply it to sort of the obvious place here, then we're left with these two nodes, which we can cover with our sort of unit templates here. And that works, but this is a situation where the greedy approach does not lead to the optimal solution. As you can sort of see, the other two shapes are in fact the one that leads to the optimal solution. We can cover this tree with two shapes using the triangle over here and the sort of the bar over here. And the classic way to solve this problem is with dynamic programming. And so the way this works is, you're probably familiar with dynamic programming, is you want to basically divide and conquer the tree. And so the trick here is that there are many ways to divide this tree into a bunch of little trees. In fact, there's one for each possible location that we could, for each one of these shapes that we could apply at the root. So someone has to cover the root, right? So let's just pick one of these guys. Let's say the triangle, right? And that's going to cover the root. And that leaves us with a bunch of other trees. And this problem happens to have what's called the optimal substructure property, meaning that if we are assuming that the triangle is going to take the tile here, then the optimal solution with the triangle here is the triangle here and the optimal solutions of the trees, right? And so that is a classic tell that we're going to use a dynamic programming approach. So we're going to memoize all this stuff, and it's going to be super fast, and it's going to give us the optimal solution. Okay, so let's move on from instruction selection, but we're going to see some of those themes pop up later. All right, so now we're back on the transformation side of things, and we're going to talk about e-graphs. This is sort of the core of what I've been working on for the past couple of years. So let's dive in and see what the heck is an e-graph. Well, you'll see that it looks a lot like an AST. In fact, sort of any AST can be lifted pretty trivially to a sort of very, very simple e-graph here. But one thing to note is we've got two parts here. We have our sort of nodes, which are the nodes from your AST, but they're grouped into these e-classes, or equivalence classes. And the point of this is that we're going to store e-nodes that we consider equivalent in the same e-class. Okay? Note that we don't really have any equivalences here because each e-class only has a single node in it. So how do we get more than one node into an e-class? Well, first I should introduce the notion of representation. So we say an e-class represents a term if you can sort of follow the edges and find that term within the e-class. So here we got this program a times 2 divided by 2. All right? And say we want to try to optimize this to a, right? We want to cancel out the multiplication and the division. Okay, so we're going to approach this, spoiler alert, via transformation, right? We're going to use rewrites to sort of iteratively grow this e-graph. All right, and this is going to look exactly like term rewriting, at least at the start. We're going to look for instances of the left-hand side inside our e-graph. Hey, I found one. It's highlighted in red here. It's our a times 2. That's going to give us a substitution, which we plug into the right-hand side, and so on. The difference is that instead of destroying this times and replacing it with the shift node, we're going to add the shift node to the same E-class. Okay, this is registering that, hey, I've learned now that A times 2 is in fact equivalent to A times 1, or sorry, A shift 1. And this is great because we've done the rewrite, we've learned the new thing, but we haven't forgotten the old thing, right? So what we're doing is we're taking term rewriting and we're shifting our state space. Remember I was talking about how much stuff are you willing to hold on to during a search? Here we are going to be willing to hold on to a lot more stuff. Now we're going to do our best to represent it compactly, but ultimately that's the trick we're playing, is we're growing our state space. So now this E-class represents A times 2 and A shift 1, all right? And the nice thing is that this notion of representation sort of bubbles up, all right? So you can see that this E-class over here, despite only having one node in it, represents 2 programs, okay? And I don't want to belabor the point here, but the point of the slide is that even if we applied this rewrite here, A times 2 goes to A shift 1, which, not a bad idea in general, but it is a bad idea if you're trying to reduce this A times 2 divided by 2 to A, because you sort of lost your multiplication, and it's going to be hard to cancel that shift later on. Even if we apply that, we haven't lost our handle on this multiplication, so we can eventually apply these other rewrites and prove that A is equivalent to our input. Okay, I'm just going to skip this slide for now. And the final component of this sort of algorithm, if we want to use this for optimization, is called extraction. And, well, we've made this big E-graph, but the point of program optimization is to have a better thing come out at the end of the day. And so we need to sort of do that last step. So we need to remember where we put our input. Somewhere in this E-class, our input is represented, A times 2 divided by 2. And here we simply want to pick the smallest member of that E-class. Now in this case, it's simple. We have the leaf A here, so it's not a whole lot to say. But in general, this is solved by a dynamic programming algorithm that looks very, very similar, actually, to the one that we saw before. OK, and so that's the equality saturation workflow. To sort of put it all on one slide, you take your initial term and you chunk it into an E-graph. It looks like that sort of basically AST-like E-graph that we saw on the first slide. And then we start turning that crank, OK? And here, when we do our rewrites, this is no longer well, it is a search procedure, but it isn't, there's no backtracking needed. You don't have to worry about taking a wrong turn because this is a monotonic process, OK? When we do a rewrite, we're only adding information. Our state space is only growing, and so the price is that our state space might grow a lot, but we don't have to worry about taking wrong turns. And then when we're done, we can extract an optimized program. And because we've only sort of taken steps that put equivalent things into equivalent E-classes, we have, in fact, you can generate a proof that the optimized term is equivalent to the input term. All right. So let's move on to the final step of our tour here, which is query optimization. And I thought I had animations on this slide, but instead you have to look at it all at once. So this slide is basically giving a very abbreviated version of what is called the volcano optimization architecture from query optimization. Now don't worry if you're not familiar with SQL or databases or any of that, because we're not going to really even be thinking about it. I've sort of boiled it down to its essence here. And its essence is just a dynamic programming problem. But it's powered at the top level by rewrites, which I think is very interesting, and which is why I included it in my talk here. So let's take a look at this. So when we want to optimize some query, right? And for our purposes, we can consider a query a program, right? It's a thing that we want to make go fast, right? So that's what we're going to do here. So we want to optimize this query, and what are we going to do? Well, we're going to approach this with dynamic programming, so we need to figure out a way to sort of decompose this into smaller problems. Now, one way to do that would just be to look at the query and look at its children and optimize the children, and then put those right back as the arguments. But that's not enough because you might be able to transform this query at the top level. Okay? And so the first thing that the Volcano system does is it builds a set of possible rewritten queries. And so we're doing term rewriting here. These queries are exactly term rewrites that we saw before. And we're building all of the possible things that this query could be rewritten to, but we're only doing rewriting at the top level. Okay? We're not going to worry about rewriting the subterms because we're going to get there recursively. Okay? So, if we, changed from the language of relational algebra to, arithmetic or something, then, maybe the input program is, I don't know, A plus B, and one of our rewrites says that, hey, you could also rewrite that as B plus A, right? Or maybe reassociate those additions or something like that. Okay? So now we have all of the programs, the queries that have been rewritten at the top level. And then from here on out, this is just bog standard argmin, right? We're just going to loop over them. We're going to call optimization on the children and take the cost of the resulting query. And if it's better than the best one, update. So this sounds like a really simple algorithm. And I have bulleted it down a little bit here. But this is really the essence of the Volcano system. And this is more or less, modulo a couple optimizations. The state of the art in query optimizations. So rewriting plus dynamic programming, if your cost function is friendly, if you're willing to accept some level of backtracking search in the sense that you are going to recurse on a couple different children here, can get you a long way and be state of the art depending on your domain. Okay. So just to wrap up, some of the themes that are exciting me currently in program optimization are basically these things I talked about. Thinking about program optimization, both in terms of the way that we think about it in terms of compilers, but also looking into other domains and being inspired by the sort of search phraseology. So program optimization is search. If you can avoid implementing it as a search, that's a really good idea if you can get away with it. But there's a lot of important context when you can't. Okay? And when you can't, you can look to sort of these two schools of building a search procedure, and in fact, you can combine them to build a really effective program optimizer. And again, the questions that you have to answer along the way can really result in vastly different looking algorithms. Are you going to only consider one program at a time or many? Are you going to store these programs over space or over time, right? Are you going to have a set of programs like in an eGraph? Or are you going to have a backtracking search that sort of, maybe rewrites in this direction and then rewrites in that direction? And finally, one thing that I didn't get to talk a lot about is, well, optimization is about minimizing cost, right? And the properties of these cost function are very interesting and important and can change what you can do in your algorithms, right? We saw how in rewriting, these cost function can get baked in to your rules, right? Like you want to prove a term rewriting system terminating. Well, all of a sudden, now like the proof that your term rewriting system terminates takes into account properties about your cost function. And we talked about eGraph extraction just a little bit, but our dynamic programming algorithm for that only works for certain cost functions. If it doesn't have certain nice properties, then we have to resort to a much more expensive algorithm. So it's also worth keeping in mind the properties of these cost functions. Okay, that's all I've got. And just a quick shout out, because I didn't get to go to the earlier session. I am recruiting this year, so if this stuff sounds fun, I hope to see your application this cycle. All right, thanks.
Great, thank you. I think we have time for one or two questions.
Hello. Do you know about instruction combining or inst combining in LLVM?
Yeah.
So, does this have potential to replace that huge pass, which is like handwritten optimizations for optimizing common patterns in terms that you see, like you showed?
Are you asking which one replaces which one?
No, can that complete pass be replaced by using this theory? Yeah.
No. I mean, okay. I think, again, a lot of the algorithms in LLVM are designed for, to avoid doing search to some degree or to a great degree, because search is very expensive, whether you're doing it in space or in time. So this is definitely one of those cases where, hey, I would love it if we could cram eGraphs into LLVM, but the performance just isn't there yet because of how much stuff we're carrying around with us.
Okay. And another question was will this apply to maybe function calls? Like if you have a function which you pass parameter A and B to it, and you know that maybe the input to it is they follow an associative rule if you pass it. So can we apply similar stuff to function calls?
Sure, definitely. Yeah, I mean, those are part of your AST, right? And if you know properties about, like, you know, the function itself, then that might give you new axioms that you can use to optimize your programs. I mean, I think, you know, extensible optimizers is one of, you know, it's definitely like a holy grail of program optimization. And I think that's something that the query optimization people actually have figured out a little bit better. Their architectures for optimization are designed to be extensible in a little bit more easier way.
Okay, thank you.
Yeah.
Thank you for the talk. That does sound very fun. I wanted to ask, when you say that, is it ever useful to have negative values in the cost function? Like, can you think of scenarios where that happens? And also, I think that where it says that if the cost decreases each time, it's going to terminate. That doesn't seem true because if the cost halves each time, it's not going to terminate.
Yeah, so I was definitely skipping over things. It needs to be, you know, a well-founded order, and then, you know, there's all these sort of, you know, sort of algebraic properties that it needs to have. But yes, so exactly, you can't, you know, Zeno yourself. If you're doing integers, then you're good to go.
Okay, but are negative values, have you seen that as a practical, like, negative costs?
Sure, I mean, negative costs can pop up when, you know, you're going to end up with something that looks very similar to negative costs whenever you have a composed program that is cheaper than any of its children, right? And so this is a non-monotonic cost function. And yeah, I mean, like, for example, the eGraph extraction stuff doesn't work with that, right? So, you know, that's one of the properties that you would really love to have in your cost function, but it doesn't always apply, right? And when it doesn't apply, you need to resort to fancier and more expensive algorithms all the times.
Thank you.
All right, we're a little bit over time, so we'll wrap up. Let's thank the speaker again. And the next session is at 4 p.m.
Okay, welcome back. So today we have with us Aus Albargoti. Aus is an associate professor of computer science at the University of Wisconsin-Madison, and he's also a scientist at Aus, or AWS. He received his PhD from the University of Toronto. Aus loves automated verification and program synthesis and thinks that they will save the world. He has applied verification and synthesis to a broad range of topics, including machine learning, robotics, privacy, quantum computing, and beyond. Aus says that he's super excited to be at PLMW, and today he's going to talk about some uncertainties in his academic career and how he has navigated through some of them.
Thank you. Can you hear me? Everyone's good? All right, yeah. So when the organizers invited me, thanks to them, of course, for inviting me, and thank you all for being here. When they invited me, they sent me the following email. It said, the goal of the talk is to raise awareness on mental health issues. And I read that and I was like, me? Like mental health? Like, I have nothing to say about mental health. Like, I can maybe tell you how to ruin your mental health, but nothing positively how to deal with it. And I was like confused. Like, I had to check, who is this email addressed to? Like, is it addressed to me, or is it like they're looking for an expert? And to my horror, it was actually addressed to me. And, but then, the next part of the email said, of course, you are much welcome to pick your own topic of interest. And I was like, I can talk about whatever I really want. So, my love is, again, static program analysis. And the best way to do static program analysis is abstract interpretation. So let's start with the very basics. This is a joke. We're not going to do this, yeah. But I mean, ultimately, we all know what a Galois connection is, and this is not what this talk is about. Let's see. Oh, there we go. No, seriously, when I got that email, I started to reflect upon my own journey from being a graduate student and being an assistant professor, then being, a tenured professor, and I identified like one recurring theme, and I didn't know how to put my, my hand on it. Like, is it? And what I thought about is, I think it's uncertainty. Right? That's how I defined it. And if you look at the dictionary, if you check Wikipedia, or if you ask ChatGPT, what you will get is something like lack of knowledge or predictability. That's the definition of uncertainty that's out there. Okay? But I'm going to strengthen this definition a little bit. After all, I'm a formal methods guy, so I love definitions. They have to be tight. You can't let anything go. So I'm going to strengthen it a little bit. And the reason I'm going to strengthen it, because I wanted to identify with the nuances of human psychology, or at least my psychology myself. So specifically, I'm going to say there's no clear path to acquiring the knowledge. So not only do you not have the knowledge, you don't know how to get the knowledge. Right? So there's two layers to it. It's sort of like there's a lack of agency. Like, I can't do anything about it. Yeah? So let me give you an example. Like this morning, I did not know how to get to PLDI. I did not know how to get to this hotel. I'm not staying in this hotel. Okay? So lack of knowledge. Right? But I had the tools to acquire that knowledge. Could have checked Google, could have asked a local, could have looked for some nerds with name badges and followed them. It was easy, right? But imagine if I woke up this morning and I did not know where PLDI was, and I had none of those tools. It would have been scary. I would have felt lost. I would have been like, I need to get to the stock, and the organizer would have been freaking out, and it would have been a mess, right? So really, like the way I think of uncertainty, it's kind of a lack of bearing, right? You're lost, and you don't know what to do. And when you're lost, it's frustrating, it's scary, but can also be a great time of exploration and discovery. Let me give you another example of why I think this definition is a good one for uncertainty. I mean, if you think about it, humanity has devised so many ways to tackle those two questions. We have religion, we have philosophy, we have the sciences, right? So for example, some religions address the lack of knowledge by giving us a very clear story of what comes before and what comes after. Other religions, and perhaps modern interpretations and forms of meditation, address uncertainty by targeting the lack of knowledge or predictability and helping us live with it. They'd be like, we don't know what's going on, but we have to cope with it and live with it and be one with it. Science, on the other hand, does not provide us knowledge right away. It provides us a path, not necessarily a clear path, but a path towards acquiring and systematizing knowledge. Okay? But this talk is not about the existential questions of life. this talk is about my own journey with uncertainty in my scientific career. And it's not meant to be an advice talk, like take this and go with it. It's really just, my hope here is for some of it maybe will resonate with you today, some of it maybe will resonate with you in the future. Okay? All right. So let's start at the very beginning, right? The year is 2008. The city is Toronto, Canada. And it's late August, early September, the end of summer in Toronto. And it's a really magical time. It's the kind of magic that you can only get at a place that experiences a long and harsh winter. Right? And I've just arrived there. I'm barely 21, head full of hair, and yeah, and I'm really excited to immerse myself in computer science research. Right? So first thing is orientation week. And in orientation week, I got to meet all these graduate students who had come from all over the world and all over the country, from the US, from Canada, from Europe, from Asia, from the Middle East, from Africa, and it was just incredible. I was like, wow, all these people came from all around the world to be with me, to study computer science. That's amazing, right? And I was like in nerd heaven. And and then I remember the first meet and greet with the professors, and it was what is now called the PL and software engineering group. And I was talking to all these professors, and I was talking to the existing graduate students, and I was over the moon. I was like, wow. I called my parents right after, and I was like, everything is amazing. Everyone is awesome. I love it here. Right? Then the semester started. And all the good stuff that you get at a CS department. We had the classes, we had the talks, we had the seminars, we had the graduate student mixers. We were going out and having fun, and it was exhilarating, right? And I was housed in this beautiful office, which the PL group still lives in the Bayhin Center in Toronto. Very startup-like office, very energizing. And I was surrounded by all these incredible graduate students, the second and third and fourth year. And because it was September, they were all coming back from internships, from Microsoft Research, from NASA, and it seemed like each and every one of them, had something going on. Like one of them was writing a paper, one of them was traveling to some, exotic country to present a paper, one of them was coming back from a country after presenting a paper, and I was looking at them in awe. And I was like, wow, how can I be like those people? For me, they were just a completely different level, and I was lost. I was just barely 21, right? And that was, my first brush with uncertainty. I was like, how do I do research? I'd come to graduate school to do research, but I had no clear idea of what research involved. I did not know what research is. Of course, I had seen papers, I'd read papers, but I did not know what the process of research was like. And I was looking at those students, and I was like, I want to get there, but I just don't know how to become like them, right? So I did not have the knowledge of research. That's number one, lack of knowledge. And I did not have a clear path to acquiring that knowledge. Now, of course, I had a guide, which is my advisor, Marcia Chechik. So she gave me a bunch of papers to read, and I was reading them. And I was understanding them. I had, the mathematical maturity to understand what I was reading. I was looking at, algorithmic verification. And, but I had no clue how to go from reading the papers, reading the existing knowledge, to constructing new knowledge, right? I just did not, I could not bridge this gap. I did not see what's going on, right? And I remember, one of my first meetings with Marcia in September, right? And I asked the most naive question ever, which is hilarious. And I always think about it, and I'm embarrassed by it. We were sitting in her office. I'm sitting in the guest chair, and she's across of her desk. And we're having a technical discussion about one of the papers I was reading. And then towards the end, she's like, well, what else should we talk about? I was like, oh yeah, when do I write a paper? And and notice that I used the word when, not how. Because I was looking at all these students and they're writing papers. I was like, my time is going to come anytime now, right? And Marcia, in all her wisdom, just leaned forward and smiled, and she said, "When you have something interesting to say." And I keep thinking about that, and at that point, I did not have anything interesting to say. At least I could recognize that, right? I did not have anything interesting to say. And I was feeling lost, right, as a result. I wanted to have something interesting to say, but I had no clear path towards that. And feeling lost, is an extreme situation. You don't want to be lost, right? No one wants to be lost. But extreme situations lead to extreme reactions. And my reaction was to just immerse myself in the research, right? I was like reading papers, watching talks, going to talks, reading books, talking to students, looking at PhD theses, et cetera, et cetera. I was just like doing all this stuff. And I was going and going and going and coming up with ideas and iterating on those ideas and talking to my advisor and talking to students and iterating and trying and iterating and trying. And the key word here is iterating, because research is ultimately, it's not a linear process, right? And you have to keep refining and refining and refining. But I just did not know where I was going. I would come up with stuff, but I had no clue where I was going. I was on this like beautiful trail of math and algorithms and logic, but I just did not know what to look for on this trail. So I was feeling, quite lost. All right. So this kind of uncertainty of what is interesting, like I did not have the taste for the interesting, right? And persisted for the first couple of papers. But I had a guide, and the guide was my advisor. But my advisor ultimately was, a closed box oracle, right? Full of, insights and knowledge and heuristics developed over the years, right? And I can't just like look into that oracle and take all that knowledge in one shot. My only interface to that oracle was I would give it my current state of research, and it would output a next step for me to do, like run more experiments, prove this theorem, make this algorithm fast, and maybe at some point the oracle would tell me, you have something interesting to say, go write it up, right? So I understood that my job was to keep querying this oracle until I could build my own oracle inside of my head, right? So that part I understood, but I still did not know how many times should I query this oracle until I get there. So again, the uncertainty persisted. I would say for the first couple of papers, I was just like churning, but not knowing where I was going. And then later, as a graduate, as a faculty member, I tried to work with my graduate students to help them with their own uncertainty. Because for them, I am a closed box oracle, right? And they would come to me with, like, let's say, experimental results. And I would be like, run more experiments, run more experiments. And the process might go for weeks and months. And for them, it looks like I'm a madman. I just keep telling them to do more stuff, right? Like, what's the end, right? And I try to explain that ultimately there are things that I cannot necessarily be able to explain. I try to explain the things that I know, or like that have rationale to them. But ultimately, it's an exploration process, right? And we have heuristics, and I have developed my own heuristics. And they're trying to kind of develop their own heuristics by querying me. Anyways, long story short, at some point, I had something interesting to say. And I was told, go write it up. And that's when the next uncertainty came about. How do I write a paper? Now I have something interesting. How do I write a paper? I read, of course, tons of papers, but I did not know how to write a paper, right? I did not have that knowledge. And I did not have like a clear path towards acquiring that knowledge, right? Like there's no like, do these 3 exercises every morning and you'll be writing PLDI papers by the summer, right? Like there's none of those. Like there's a lot of like how to get 6-pack abs by the summer. None of them how to write a PLDI paper by the summer. I don't know why. So I was kind of, again, I was in this limbo. And so what did I do? Well, same thing I did before. I immersed myself in the process. Specifically, we were submitting to a conference called CAV, Computer Aided Verification. And what did I do? I just printed out all the CAV papers I could print. And I had a stack of CAV papers this big. And I remember sitting in a coffee shop in Toronto on a couch and just going through each and every paper, right? Just like trying to understand how are these papers written, right? Like I was just trying to understand the structure. Like what's the first sentence of the abstract? What's the second sentence of the abstract? How does the conclusion look like? How do they present the results? How does the algorithm look like? And it's incredible thinking about it right now, like how foreign a paper was to me. The structure of a paper, it was like completely foreign. Now it's second nature. So I was treating my mind like a large language model, and I was just fine-tuning it on these CAV papers at a coffee shop. And at some point, I fine-tuned it enough that I decreased the uncertainty to a point where I could start writing myself. And then, I started writing. And I wrote, and I wrote, and I wrote, and I came up with a paper. The paper got accepted, and on and on and on. So that was my experience in, whoops, something happened? It's back, cool. That was my experience in graduate school. But one thing I want to touch upon here is that the uncertainty in personal life can also affect your life as a researcher, as a scientist, as a student. And I'm going to give you one story from my own life that did affect me. So in my third year, in 2011, I went for an internship at Microsoft Research in Bangalore, in India, in particular. And I had a wonderful time. I met all these amazing friends that I'm still in contact with. Actually, the other day, I messaged one of them because he knows about Copenhagen. He gave me some great advice. And I made some, my managers there became lifelong mentors. I actually published my first PLDI paper out of that internship. It was just an amazing time. But in my first few weeks at Microsoft, I got sick. I got like cold and flu symptoms. I had a fever, I had chills, I was feeling cold. I went to the doctor. They did some blood tests, and they're like, looks like you have an infection. It's likely typhoid. Here's some medicine. He gave me the medicine, and my fever subsided, so I thought I was getting better, but I simply did not get better. Right? I just had, constantly was fatigued. I had chills. I was like feeling cold all the time. And I had the funniest thing ever called restless leg syndrome. Does anyone know what restless leg syndrome is? As the name suggests, you just have the urge to move, right? So I'm tired, and I have this like relentless urge to move. It's like if a comedian was coming up with a disease or a medical condition, they would totally pick that like as the #1 symptom for their comedy show. So I had like this, so I was in my, in the internship, I was writing some OCaml code, and I would just get this, urge to move, and I would start moving. And the office was too small at the time, so I would just go to the roof. Hence, the roof. This is the roof of Microsoft Research, the old building. I realized when I'm preparing this talk that I have just so many pictures from the roof because I was on the roof for so long. And all throughout the internship, I had this persistent, of course, uncertainty, which is, what is wrong with me, right? I did not know what was wrong with me, so lack of knowledge, and I had no clear path to acquiring that knowledge. It seemed like even the doctors didn't know. I kept going to the doctor, more tests. Everything looked normal. I was fine. And then I went back to Canada. My internship was over, and went to the doctor there. And again, they looked at all my tests, and they did some more tests. And they're like, look, everything is fine. But from your test, it looks like you got a viral illness at some point. You're recovered. And these are the post-viral symptoms. Kind of like long COVID, where you get COVID, you recover from COVID, and you just have this long time with symptoms. So I was feeling miserable for a pretty a long time. But the symptoms would continue to subside until, I would say, the end of my graduate student career. But it was a really tough time. Ultimately, the uncertainty took up a lot of mental space. It's not really the physical toll of the symptoms. They weren't that bad. I was just feeling cold and fatigued and so on. But I could do work. But it's really just the mental space that it took was just enormous, right? Because I did not know what was wrong with me. And it looked like no one knew what was wrong with me. So I think in retrospect, if I did not have that episode with the infection, I would have probably been infinitely happier and maybe twice as productive as I would have been otherwise. So that's how your personal life, of course, can affect your career as well, your scientific career. All right, so back to grad school. During grad school, I did not know what I wanted to do. So I did not think of the problem much. Like, do I want to do industry? Do I want to do academia? What do I want to do? But then towards the end, my heart was set on academia. And I don't know why. But I think in retrospect for two reasons. One, I always had I always wanted to be at the forefront of knowledge, right? Like I wanted to know more than anyone else. And academia was kind of the right place to be there. I also had a lot of ideas, right? By the time I was about to graduate, I'd accumulated a lot of ideas. So I was about, and academia was the right place to hire a lot of students and have them work on many different things. So my heart was set. And I was like, I'm going to do academia, and I'm going to become a professor. And I did not consider any other option. In fact, I was getting calls from this Google recruiter. And I was like, hello, no, I'm going to become a professor. Thank you very much. Boop. And it's over. Okay? So what did I do? I prepared my applications. If you don't know how the academic job market works, usually it works like this. In November, you submit applications to the various universities that have postings available. And then in January and February, you start getting interviews. So I prepared all my application materials, sent them out in November, and then the wait began. Specifically, I sent out 30 applications. I remember I found the spreadsheet from back then. So I sent 30 applications. I was like, I'm going to become a professor, right? So I spammed all the universities that were hiring anything remotely close to pretty much every university is here. In Europe, in US, in Canada, whatever you like. So I submitted all these applications, and then the wait began, and the uncertainty set in, right? Will I become a professor? At this point, I did not know. And at this point, I did not have a clear path. It was completely, I did not have agency at this point, right? Applications are out. I couldn't do anything about it, right? All I could do was wait. So the wait was killing me, right? December had passed, then January began, and nothing. No emails, no phone calls, nothing. And then some of my friends started getting phone calls and emails and invitations for interviews, and I was like, ooh, looks like I'm not going to get any interviews. And then, end of January, nothing. And then, beginning of February, nothing. And then I get this email from the University of Wisconsin, and it brought me back to life, right? And of course, I still did not know whether I'm going to become a professor. I could just watch the interview. But I had a clear path. I had agency. I had a clear shot on goal. I could try. And that changed my mindset, because it kind of nullified the second part of the uncertainty definition. So I prepared, went, gave a talk, got the offer, and moved to Madison, Wisconsin. And that was the only interview I got. So, moved to Madison, Wisconsin in January of 2015, in the dead of winter, right? And no one had told me that the semester starts on January 20th, and I arrived on the first Monday of January. And it was no one was there, and it was so cold. It was about minus 20 Fahrenheit, which is equivalent to minus 20 Celsius. It was very cold. So I show up, no one's there. I go to the department. Thankfully, the department manager was there. I was like, I'm the new professor. He's like, oh, here are the keys. Office is over there. I go to my office. There's a chair. There's a desk. This is the desk that was there. But there was no chair. So I had to go around this building in January when no one is there looking for a stray chair to steal and put in my office. And I was like, wow, what an anticlimactic end to my journey, right? Anyways, so I found a chair, and then the first thing I did was slightly modernize my setup, just a little bit. So I just bought a new desk and a new computer and got going, right? And when I was a graduate student, the foremost uncertainty was, how do I do research? How do I write papers? That was my kind of big thing. And then when I started as a faculty member, it was like the fire hose of uncertainty, right? How do I hire students? How do I get money to pay those students? How do I find ideas for students? How do I find good ideas? How do I find many good ideas in case those ones don't work? And how do I keep those students happy? And how do I help them progress with their career? And how do I help them to teach them to write and read and present and on and on and on. It was like an infinite list of things. And I'll just cover one of them right now, just for the sake of illustration, which is how do I write grants, right? So to raise money in academia, you have to, to pay students, you have to raise money. And to raise money, you write grant proposals. Roughly speaking, a grant proposal, at least in the United States, is like 10 to 15 pages of like describing a problem that you want to solve. And you have to write it convincingly that it's a hard problem, it's an interesting problem, and taxpayers should give you money so that you work on that problem. But unlike papers, there aren't even examples online, right? Like people don't share them publicly. They don't put them in their website. So no one could tell me like how to write a research grant proposal, and I'd never seen one before. So I had this new uncertainty. But it was a very similar uncertainty to what I faced as a graduate student. I didn't know how to write papers. Now I was faced with a new one. How do I write grants? Very similar. And my reaction was actually very similar as well. I immersed myself in the process. And I did exactly the same thing like when I was writing a paper. I emailed a bunch of professors that I knew, both at Wisconsin and elsewhere. And I told them, can you please send me examples of research grants that you've written successfully? And they sent me a bunch, and I have printed out a stack this big of research proposals. And I started going through them one by one. Again, training my LLM, fine-tuning it on this stack of proposals, trying to understand what the heck is a proposal, right? Like what does it even look like? And I kept going and going and going and going until I sort of like extracted a template of sorts, right? And a philosophy. And in fact, actually, I have a physical template, like a LaTeX template, that has proliferated at this point. And a lot of proposals look like mine at this point. So one thing I want to point out here is that notice with both like research, with writing papers, and with getting funding, I kind of deployed the same strategy. My brain had developed this funny pattern which said, if you're faced with uncertainty, meaning something that you don't know how to do, immerse yourself completely. Okay? And it worked all the time. Like in this very case, I was going to the office really early in the morning, and as you can see the morning light here, that's why I have this picture. Because I wanted, I did not know how any of these how long any of these tasks would take, right? Like I had to learn how to write grants, I had to prepare my class, and I had to do research simultaneously and do service and hire students and so on. And all of these things were new, and I did not know how much time to allocate to each, and when will I get to the point where I could write a grant proposal. So I had to like go really early in the morning to do that. But this kind of simple approach of if you're faced with uncertainty, immerse yourself in the work, while it worked for me, I don't think it's particularly optimal or healthy. Since then, I've been kind of more deliberate about it. I've been like, whenever I face uncertainty, I ask myself, how can I break down this task? Is there something better than printing out a stack of proposals and reading them one by one and trying to extract a method in this madness? Anyways. But as a professor, the overarching uncertainty is not how to write grant proposals, is will I get tenure? Right? And let me explain the tenure system for if you have not heard of it. This is true in the US, in Canada, and many places around the world, including some places in Europe. But roughly speaking, you have 6 years of being an assistant professor, right? 6 plus or minus, depends on the place, but 6 is the average, I would say. And then in most research-intensive universities, at the end of those 6 years, you're judged on your research. So they ask for experts in your field to comment on your work and so on and so forth. It's a very rigorous process. And there's 2 outcomes. You either pass and you get tenure, and therefore a job for life at the university, or you fail and you're out. That's it. Right? So it's a scary process, right? And it ultimately hinges on research. And research itself is highly, highly uncertain. Like each step of the way, it's uncertain, right? So it's a very uncertain process. So let me explain. I'll give you a caricature of what research looks like. Okay? First, you get a good idea. It has to be good and has to be new. Then you develop that idea. Then you publish the results. Very easy. 1, 2, 3, right? But every step of the way is replete with uncertainty. First of all, how do you get a good idea? Actually, what does that even mean? What is a good idea, right? How do you, like, you have to conjure up something out of nothing, right? It feels like you're defying the laws of physics when you come up with a good idea. And then sometimes you have a good idea and you start developing it and you realize either it's actually not a good idea after all, or maybe someone had beat you to it, or sometimes you simply do not have the tools to develop this idea further. Maybe it's just ahead of its time. Okay? And then if that happens, you go back to step 1 and you look for a different new idea. Right? And sometimes you develop your idea and you're so happy about it and you submit it for publication. And then ultimately, publishing a paper in a conference like PLDI, it's a social process, right? There's no guarantees, right? Your paper might get rejected, might get accepted. Of course, eventually, good papers get accepted, but there's no physical law that says that good papers will get accepted, right? And there's no social contract. Like, no one essentially will get your paper accepted after some time or anything like that, simply. Okay? So the entire process, and then if it doesn't get accepted, you might have to either resubmit it or develop the idea again, or maybe give it up altogether. So the entire process is replete with uncertainty. But the ultimate uncertainty is at the very top, is getting a good new idea. It feels so daunting, to come up with something new and interesting. And when I was preparing this, I remembered this discussion that I was having with a senior colleague at some point. He's not a PL professor, but he's in a different field, top of his field, senior professor, books, papers, awards, commercial systems, whatever, like all the greatest CV ever, right? And we were talking about the research process and what it's like and coming up with ideas and so on. And he told me something that stuck with me. And he said, like every time I'm done with a paper and I submit it for publication, I get this feeling that I'll never have a good idea again, that I've run out of good ideas. And I was like, wow, you have this professor who's like top-notch, top of his field, like crippled by the anxiety of coming up with a good idea. Anyways, long story short, I got tenure. So yeah, towards the end of my, I would say my 5th year as an assistant professor, it was clear kind of that things were going well, right? So I mean, it was clear that my tenure case will, I would say 99% make it. So I should have been excited, I should have been relaxed, should have been popping champagne, but none of that. It was actually the opposite, A new wave of uncertainty hit me. So you see, when I was an assistant professor, it's like it's a time trial race. You have 6 years, you have a ticking clock, and and it's like, all right, go do some research, and in 6 years we'll see you and we'll judge you, and you just go, right? Like you make some bets about what problems to solve and what to do within those 6 years, and you just go for it. Like there's no room for thinking or strategizing. You do something that you trust your gut instincts, right? This short amount of time. But now with tenure, with a job until the end of times, I was faced with this overwhelming task of optimizing my career over a 35-year time frame, right? It's a very unconstrained optimization problem. And unconstrained optimization problems have so many possible solutions and so many possible paths, right? What should I do? And I did not know. And interestingly, when I was thinking about this period of my life, I found this photo. And this photo was taken 2 weeks before the pandemic hit the United States. We were in Seattle for the PLDI PC meeting, the program committee meeting. The last physical one. And then after I took this photo, I went out for a walk with Ishil. I don't know if you remember. She's over there. She's going to be on the panel. You remember? Yeah. We went for a walk, and and I was telling Ishil, like, I don't know what to work on. Like, I don't know what to do, right? So the unexamined life, as Socrates told us, is not worth living, right? So I was re-examining my life, okay? And I was facing this deep uncertainty, which is like, what should I do? and I did not know what to do. And what I realized, at least in retrospect, is that I needed to define what my values were as a researcher. Right? Like, what was I optimizing for? Right? And was I like optimizing for deep and beautiful mathematical results? Was I optimizing for societal impact? Was I optimizing for educational impact? Or was I optimizing for academic, industrial impact? And of course, you're never optimizing for one of these things and only one. You're optimizing for a weighted sum. And my task was to find the weights to assign to all these possible values. So that's how I went about it. I was reading books and talking to people like Ishel and others to try to understand, to find what are my values. I did not know that. And I had no clear path of necessarily acquiring it. There's no, universal philosophy of life, right? And there's no universal philosophy of how to live your life as a researcher. But I went about it, and I kept searching and searching and searching for my values. Now you could say, I was, come on, like, are you saying like you never thought about your values as a graduate student or as a tenure track professor? And I'm like, no, of course, I had values, and I had guidelines, and I had principles, and I had interests and curiosities that guided me in my research process, in my choice of problems, in my advising, and in my teaching. But they were overshadowed by immediate concerns. When I was a graduate student, I was trying to figure out how to become a researcher. So I wasn't thinking this big, grand questions about what am I going to do, for 30 to 40 years or whatever, right? And when I was a tenure track professor, I was in this time trial race, and I had to make, short bets that would pan out within, that are realistic and would pan out within, 5 to 6 years to keep my job. But now with all these constraints gone, the question of what are my values arose to the forefront, and I was facing it firsthand. Right? So what are my values? Well, that'll be PLMW 2025. So with that, my advice is that there's no advice, but you will face uncertainty in your academic career, and may you face it with grace, and may you actually find joy and meaning and beauty in it. And that's it.
Open up the floor for questions. Sure. Any questions?
Yeah.
So I know I'm not one of the PLMW students, but something that I've sort of encountered in your talk here, which was great, and also in the RTFM session this morning, is that a lot of these discussions tend to come from people that are on the other side of that uncertainty. They've succeeded, and so there's always some survivorship bias that comes into maybe the. Can you, and I know it's hard for you to maybe do this on your own, but can you kind of think about maybe your experiences? You're very well connected in the community of like things that other people might have also tried to navigate this uncertainty. I always tell people that, just like you said, uncertainty is the biggest thing that you have to deal with as a researcher. What other approaches might there be?
Yeah, I mean, I don't know how to answer your question. It's a hard question because it's like a counterfactual, right? Like, I mean, I was like on the verge of not becoming a professor, for example, right? Like I only got one interview and I had to go for it, right? And then I had this choice of like, what should I do? Like, should I look for a postdoc? Should I go to industry? Should I go back to that, like, how do I go and talk to that Google recruiter again with my head down? So I don't know. Like, I mean, I imagine these scenarios counterfactually, but like, I don't know what I would have done in those. I mean, I would have been a different person, and maybe there is a part of me in a quantum multiverse that, yeah, so I don't know. Yeah.
Thank you for the talk. One question I have is, in the periods of highest uncertainty, how do you recognize where you are in the cycle from the big question, like, how do I write a paper, to, I've done it and I've sort of overcome this hurdle that I was super uncertain about.
Right.
You know, within these, and then you said multiple stages of career.
Right.
How do you identify, you know, the start point and the end point of these uncertainties?
Yeah, I guess it's kind of just like, you know, with statistical uncertainty. If you see enough points at some point, you think you did it. Like in my case, like I think after I wrote the first paper, I thought I was like, I figured it out, right, as a graduate student. But then the second paper was actually harder to write, just because of the topic. And it was kind of back to square one, where I was like, I don't know what I was doing. But then after, so those two, perhaps like those two initial papers, and maybe three, you know, I found a line of best fit that worked well. But you know, it could have been different. Again, maybe I was lucky to find those 3 points and extrapolate from there. Yeah.
Sorry, while we still have Q&A, can I please request the next panelists to take the stage?